this computer. So let me go ahead and kind of tell us a little bit about what to expect today. And let me hold on. Okay. What to expect today. I'm gonna go ahead and share my screen, and then I'll introduce myself in just a moment. Um, and I wanted to say thank you for being here. And I hope that this is a fun time for you. Let's see. Those of you that have been here before, you know that we put everything on Mixtape Sessions GitHub repositories. Pretty much everything. So there's now a nice little collection of GitHub repositories by other people. I won't go through those. We have one more coming. It's by Peter Hall, and it's not there yet. So there's his IV one, his Shift Share one, and then we have one on design. It's coming, but I'm not gonna bore you with it. These are mine. These are the two-part series. It's actually a three-part series, Causal 1, 2, and 3. We decided to break it up. Originally, it was just one big causal inference workshop. And as I continued to sort of add stuff to it, it felt too large. So now we have three, and it could keep getting larger. Because I love adding to it and learning new stuff. So here's the link there. That's where we're going to be. Also, let me go ahead and give you the Discord link now. And as people come in, I'll just kind of add them. If you see somebody come in that's not there, if you wouldn't mind just sharing that with them. But I prefer to have us speak inside the Discord channel. So, the Discord channel, you can see I have like a bunch of them here. They stay alive for a long time. So these are all previous workshops that I've done. Looks like somebody's left me a little note in there. But it's a way for you to continue to interact with people after the workshop is ended. And we're going to start. You can put some general stuff in here. It looks like Kyle's kind of added in a lot of general stuff. We got the Zoom link. I've also put the Zoom link here. We got our course material here, which I just gave you. There's a STATA license that you can use. And he's pinned all this. But I'd like us to spend our day in day one, but we also have some networking. So if you wouldn't mind introducing yourself in the networking section, that would be great. And the thing I would just ask is try to be your friendliest self. Introduce yourself to people. Try to help them. If you think that you know the answer. Help people. Okay. What's nice about Discord is it doesn't really feel very disruptive. Here we go. Doesn't really feel disruptive. We kind of just we sort of learned that early on. I did this workshop on Twitch back in the summer of 2020, and or maybe it was, yeah. And you could tell that something about commenting on Twitch versus commenting on Zoom felt very different. On Zoom, it was very clear it was going to me, and on Twitch or Discord, it was very clear that it was just like a joyous, all of us kind of talking. So if you think of something, offer it. And if it's not right, big deal. Okay. Well, it'll be fine. It's just, we're going to kind of help each other as much as we can and be forgiving of each other if it doesn't quite seem right. It's fine. Okay. So we're going to put that there. And if you do need the Discord link again, please just ask me. And I'll post it up 100 times, okay? I am going to have in the background, let me do one thing here. Do need to have in the background need to have the Gmail open just because sometimes people can't find the Zoom link. That has not happened yet. Good. So All right, so we'll just kind of, gotta be a way to make that. Yeah. All right. So, okay. All right. So we get started. We're going to go into slides here. There's only one slide, synthetic control PDF. It's only one. And on all of these, we put the LaTeX out there. And, you know, the whole philosophy of mixtape sessions is to be a bridge, a hub connecting these ideas and this work to as many people as possible who, for whatever reason, don't have access to it otherwise. Don't have access to it otherwise. And, you know, one of the ways that you don't have access to it is you're not physically in a place where it's taught by a professor. But another way you don't have access to it is because maybe there's like a siloed uh, you know, style of teaching where you just can't get to it, a kind of club good model. And Kyle Butts and I that run this, we have a different philosophy. We have sort of a public good model where the only club goods are the Discord channel, the live recordings, and the physical recordings or the digital recordings. Those are the only club goods. Club goods belong to members of the club, and y'all are in the club this week, this weekend. But everything else is a public good. So you're more than welcome to take this tech file and just edit it to your life's contentment. You know, change it, make it up. I really don't care. I have felt that if you start policing this stuff, it just stops being fun, to be honest. That's been my feeling the whole time is not that other people shouldn't police. That's not my place or my business, but for me, I don't like it. So this belongs to anybody that wants it. Just take this or anybody's and learn from it. Okay, that even goes for the labs. Here we've got a couple of labs that we can work through. So that's where we are. So we're going to go ahead and open up slides here. I have recently updated. Okay, so you have here slides 8 minutes ago. 8 minutes ago, these slides were updated. So if you've cloned this thing, you want to go ahead and pull the newest version. Okay, because I'm a compulsive committer. You can see here Kyle commits, but I do it constantly. So it looks like he did something. I don't know. I did much today, but anyway, so let's pull it up. And I want you to ask any questions as you get them. Okay. So anytime you have any questions, I just want you to reach out and not worry about anything regarding thinking like you're interrupting. Hold on one second. I feel like that is too low. So let's just see. We're gonna check this, see if it's too low. We have about 300 slides. It is a lot of material, but I hope that it's fun. I hope you enjoy it. Nope, that's how it works. All right. Is that how the other ones work? I feel like something's different. I just need to check my brain here. Yeah, that's different. Huh. All right, well, I'll ask okay, it's killing me. It's killing me. All right, never mind. Well, I guess on this one the thing is lower. All right, well, that's fine. Okay. All right, let's go ahead and open it up. All right, we got chat here. We're going to be using R and Stata, and then I'm going to be pointing you to some Python packages that you can use for this. I am not the greatest at Python. People have provided me with Python, but that is not my strength. And I can try to point you to some of this material where it exists in Python, but it's taking too long and slides don't download. Is anybody else having trouble downloading slides? Let me see. Download raw file. Works for me. There it is. Wonder if I could give you a Dropbox link, Zayed. Let me give you a zap. Let me do that. Yeah, it did that to me too. I don't know what the deal is. All right, well, we'll do this. Let's see how that works. That might be better. I'll add that into day one. All right. Hopefully that helps. Thank you for telling me. Um, okay. All right, let's get started. Let me kind of manage your expectations a little bit. So this is kind of what I have planned here. I've tried to organize this material in a way that I feel like tells a story, tells kind of a narrative. And the narrative that I've kind of come up with is uh, the original synthetic control model and its bias and methods to deal with that bias while still really being the synthetic control method. And then the last is that we'll do tomorrow is, and probably maybe even some of this tomorrow, is the multiple treated units and the staggered synthetic control. Okay, so there's three here that we're going to try to cover. They are the writers for sure are presenting these as synthetic control, but uh, one way to kind of group everything, both this workshop and the diff and diff workshop, is to just think of it all as causal panel methods. And synthetic control is kind of a branch of the causal panel methods that doesn't really fit with difference and differences. And I'll try to explain why that is, but there's increasingly the case that these new synthetic control methods, they can kind of, quote, do anything that diff and diff can do. And sometimes they're probably going to be used instead of diff and diff, which is really important for us to understand the assumptions and the reasoning as well as the syntax for doing them. Okay, so we'll start off here with an intro. Then we'll go into this synthetic control modifications. That's the goal for today. Then we'll look at these multiple treated units, staggered adoption. And then we'll, if I have time, I'll look at an event study in finance, and then we'll kind of conclude. And I'll be sort of updating these as I go. I'm just, like I said, I'm a compulsive tweaker, editor of the slides. So I'm Scott Cunningham. I'm a professor of economics at Baylor University. I'm the author of Causal Inference, the Mixtape, which was published in 2021 by Yale Press. I got a contract to write the second one, and it is stalled. So my goal this summer, I'm the faculty in residence at Collegio Carlo Alberto in Turin, Italy, and I am like, that is my goal. Get this thing finished. Knock it out. So I got like a lot done, but I got to get a lot more done. So a lot of what the new book is going to be about is everything that's in all three workshops. Kind of fixing stuff and updating. So I teach and host these workshops all the time. I teach them all over the world even. I'm leaving for Madrid at the end of May, spending a summer. And all June in Turin, and then a week in Scotland, and then it looks like doing it again this fall. It's a big part of my like, you know, my career or my personal mission, because I believe that, like I kind of said, and this is probably from my own personal experience, I believe that a lot of people don't have the opportunities they want to have, that they believe they need in order to be successful in their research and careers. And if that's true, I hesitate to say this, but I suspect there's a lot of inefficiencies in the labor markets. And as a result of that, some people sort of, learn this material and they didn't even know it was so different. And then others are like completely cut out. And so I say, I'm going to be this hub to kind of do this. And I've been fortunate enough that it sort of, took a little work, but I found a partner like Kyle, and it took a little work, and we have it going. So the workshops are helpful ways for you to plug into this methodological training. And the online workshops are really helpful because of all the bells and whistles you get with it. You get the recordings. It's a lot easier to do coding online this way than it is in class, is what I found. And you get a bunch of bells and whistles too, like the GitHub repositories or me pulling up videos, which I'll do sometimes. I'll do in just a minute. So it's my platform, started in November 2021. I just did the numbers. There has been 5,700. This will be like 58. This probably puts us at 5,900 people that have come to mixtape sessions, the branded mixtape sessions workshop since November 2021, and to do this kind of democratized causal inference. And the hope is that it's helping people. That's what you always hope as a teacher. So I teach them in a way where I try to cast the largest net possible and give as many on-ramps as I can. So sometimes it's kind of a slower at the beginning, and then it does kind of ramp up a little bit. And I also bring on other people. To teach, which is again part of the philosophy of just helping bridge people to the source. So I became obsessed and write about writing and teaching about this material, thinking it was important, loving it, and believing with everything inside me, because of things that I had experienced, that not everyone had the same chances to learn it. And so I tend to teach very differently. I teach very, very differently. In fact, like, I think all of my weaknesses as an economist have helped here. I've had to really deconstruct everything I learn and then re-explain it back to myself. So a lot of people say that my workshops and my writing are very heavy on the intuition, and to go kind of deep into the actual mechanics of things. It's fairly light on proofs. And that's right. So that's why I sort of see myself as a jumping board to other people's work. I do a lot on the narrow calculations. I try to do a lot of interpretations. I really emphasize the assumptions or the identification. I try to take time to code. I want everyone to at least see the code. And I'm a big advocate for data visualization. And I really try to offer my suggestions too as we go along. And when I do offer my suggestions, they're suggestions. They're not true. They're just advice. So I decided to teach this one on synth because it's a very important technique, and it's getting more and more modifications, and so I think it's a good time to have a chance to learn it. So it's 2 days long, 9 to 5, 9 a.m. to 5 p.m. We have 15-minute breaks on the hour. And then we have a 1-hour lunch break at noon. We're going to have our first break at 10 o'clock, right? Because this first part doesn't really count. And then we'll have our first one at 10. I tend to mix exposition, discussion of papers with coding and discussion, and also showing some videos if I think that they're helpful. Okay. So it's, again, just my effort to try to hit a lot of people in a lot of different ways. And then I play music at the intermission. That makes me feel, it helps me get to rest and get back. And to me, it makes it kind of fun. So that's what I do. What's my pedagogy like? So the days are long for sure. I feel like I make them less long, although I do know some people do feel like it's a lot of material. I'm a high energy teacher, but I try to give breaks as much as I can. Um, you can ask questions at any point in the Discord. My preference is in the Discord. And just one more time, I'm going to put the Discord link into the chat. So I highly encourage you just to click on that and go in there so that we have a permanent record of comments. That's the other thing. Anything that gets asked in Zoom is going to get deleted, but anything that's in Discord lives into eternity, all right, until the sun burns out. Not really. So class goals. These are my 3 C's. My goal is to instill in you confidence. Confidence to me is a feeling. It's like a self-esteem kind of thing. I want you to have good enough understanding of synthetic control so that at the end of it, it doesn't feel intimidating. It doesn't feel mysterious. You feel like you belong in the room. All right. Comprehension is the foundation of that confidence, though. You understand this material conceptually. You understand the specifics. You know what it's doing. You know what it's not doing. And then third is competency. You'll have more knowledge of syntax in Stata and R so that later you can apply this in your own work. Right? Those are my goals. All right. So we're going to communicate with each other regularly in the Discord, even after class. I'll always be monitoring it. Encourage you to talk to each other there, network. We're going to have codes and slides, and each lecture is going to be recorded. I'm going to upload it to the video as a password protected file. You can access it. You can download it. Okay. You can have it locally on your machine. Like I said, Kyle and I, we have different reasons for why we sort of have this sort of philosophy. He kind of comes from that, open science background, and I kind of come from this spiritual background. And so, they actually complement in this place. And like I said, we have club goods, and that's the stuff that's happening right now. All right, so the topics. Here's the topics. Here's what we're doing. Synthetic control, traditional. We'll spend a lot of time on that on the front end. And I'll just say it's synthetic control without any extrapolation. And then we'll do synthetic control with extrapolation and bias adjustment. Then we'll look at multiple treated units. Now we're getting stuff that's a lot more similar to diff and diff, staggered adoption, and even merging it with difference and differences. And then if we have time, some event studies. Okay, that's kind of the big picture. I'm leaving a decent amount of stuff out, but to be honest, I'm picking the stuff that I kind of believe is practically helpful. Okay, you could do a class that is on things that, at least in my mind right now, it's not clear to me anyway. It's not clear to me how I would want to, what would I want to say to someone about it? Okay. All right, so let's get started. So I put up here this phrase, warranted belief and causal inference. Warranted belief is a phrase from philosophy, from epistemology in particular. Warranted belief is like a bridge that connects a belief that you have, a true belief that you have, to knowledge, okay? And in causal inference, I tend to think of it as like having good reasons to believe that our estimates of causal effects are true. And when you have good reasons to believe them, they become knowledge. And if you don't have good reasons to believe them, it's not really knowledge, okay? So, we're going to talk a lot about what these good reasons look like. Many people, I think, especially young students, they think the good reason is to run the regression and report the table, but that's just the estimate. That's not the good reason to believe the estimate. So we're trying to kind of build the full picture supporting the warranted belief. All right. And the potential outcomes framework, what it does that we're going to talk about in a minute, it highlights this epistemological challenge of the enterprise of causal inference because of this core problem that we're going to talk about. This core problem is that you're missing some data. And if you weren't missing that data, there wouldn't even really be any warranted belief. There would just be like pure knowledge, but because we're missing data, we're sort of pushed up against beliefs about causal effects that we hope we have good reasons to believe they're true. And when the reasons are good enough, you know, you can base you can stake your life on it. Okay. So RCTs are a great example. RCTs, randomized control trials, which I hope to have my first workshop on that this fall, taught by Rebecca Thornton. She's like said she's going to do it, and I'm going to hold her to it. No, I'm not. I can't really hold her to it, but I'm going to beg her to do it. RCTs, they offer strong warrants by closely approximating these counterfactual scenarios by minimizing the confounders through the act of randomization. The magic of randomization overcomes this problem. Not completely, but it gets as close as we know to do it. So our beliefs about causal effects are probabilistic, and they're rooted in the integrity of these assumptions that we hold. The integrity meaning, are these really outlandish? Do these assumptions that we have that underlie this, can I really trust them? Should I trust them? Is there anything I can do to show that they are trustworthy? So this approach that we take, that I'm advocating that we take, sort of reflects, I think, having humility. You can have humility. You can acknowledge a study's limitations and it still be a warranted belief that you believe that it's probably true. Okay. So with this, though, you still have, this kind of approach that I'm taking. It really isn't ever probably settled as much. Maybe it will be, but the act of science is continuous inquiry, continuous collection of evidence, continuous analysis. Okay. But we're not doing RCTs. Rebecca's going to do them in the fall. We're doing quasi-experimental designs. They're still kind of rooted, the quasi-experimental designs are rooted in the experimental design. Okay. All of the, oh, does it really? Is it doing that? Oh, man. What about now? Let me see now. Let me use the microphone. See if Gilliam says it is. Okay, no problem. Okay, well, shoot. Well, when the recording is done, Caesar, it won't be. Hopefully, I switched to the microphone and I'll switch back in just a second when we do the video. So not all the quasi-experimental designs are equal. Okay, that's just something for you to kind of remember. Not all of them are equal. A lot of people will make a ladder. They'll kind of say like the RCT's at the top, and then they'll kind of like our regression discontinuity design is next. So I have like a pyramid. And then at the bottom would be something that I don't even know. I don't know if I quite like that. I mean, I do believe in the ladder. I just don't believe in the designs can only be in one part of the ladder, and some design is strictly better than another design. I actually don't believe that. All of the designs are strong insofar as their assumptions are credible. That's the thing to remember. A well-executed propensity score study could be closer to knowledge than a poorly designed, underpowered randomized control trial that didn't take a lot of care in its design. All right. It's just something for you to be thinking about, that the goal is warranted beliefs, trying to do the work extraordinarily well, support it as best you can so that the link to the work and to my confidence that this is knowledge is as short as possible. All right. So synthetic control is going to provide a pathway to robust knowledge. Frankly, one of the ways that it does it, ironically, is through a lot of data visualization. A lot of the causal inference is like that. Okay. But there's going to be various degrees of effectiveness, and the data visualization tends to be the one that creates the doubt. All right. So this workshop is going to aim to refine our use of synth towards stronger warranted knowledge. I think most people do know this right here, these like distinctions between causal inference and prediction, but not everybody. A lot of people increasingly are coming to the workshops and saying, I've not had a lot of stuff. What am I gonna be okay? So I thought I would just kind of have here this thing I got from Paul Hundermoon at Copenhagen Business School. Um, there's basically two kinds of classes, two types of academic classes. There's a stats class slash econometrics class, and then there's these advanced classes called machine learning. And you can kind of see here what goes in each of them. All right. Inside these classes, depending on the professor, you'll have classes where they're very, very clear that, something is prediction. Something is purely prediction, like the ANOVA, which I've never even learned the ANOVA because I never took these classes, but the linear regression, I obviously know. The logistic regression, I know. I did take, time series, which was pretty brutal. But then you have the stuff that we have in my workshops, which is the quasi-experimental. Well, no, the quasi-experimental and the experimental causal inference methodologies. And I have workshops just on diff and diff. I have this workshop just on IV propensity score and RD. I cover not A/B testing, but I cover RCTs in causal inference 1. That's causal inference 2. That's causal inference 1. And synthesis causal inference 3, and it's not listed here. And we do have people that teach machine learning on the platform. One of them in particular is Brigham Franzen, and he teaches a lot of this stuff. I'll teach DAGs, but nothing like the way that it's done in the machine learning community. Mine's not meant to be like that, but he'll teach double debiased machine learning, causal forests. I don't know if he covers the multi-arm bandit, but these three he does cover. But then over here, he'll also cover this stuff, even though it's prediction based. Prediction. So what is the difference between prediction and causal inference? So traditional prediction is predicting things that are real. It's predicting things that are real. It's it's looking for patterns in the data and trying to fit functional relationships between variables and a high degree of accuracy. I remember when a plane went down, a big plane went down in the ocean, and they were using advanced prediction tools, Bayesian prediction tools, to try to locate where it was. It was a prediction algorithms. It existed. It was down there. They knew it was down there, and they were trying to basically fit a lot of data and use these Bayesian methods to try to narrow down where it was, and they found it. Okay. We have a lot of that now. Even ChatGPT is a kind of traditional prediction. Okay. Does this person have heart disease? What should the next word be? What should the next sentence be? How many books will I sell? It's not predictions about the effect of a choice. It's not an experiment. It's really just more of a what's missing and can I find it using a lot of patterns in the data. So we're working on a project for the Texas Department of Criminal Justice where we're using a machine learning model with administrative data to predict who's likely to hurt themselves. And it's really kind of fascinating because the people that are getting targeted as being at risk of self-harm, they've actually not expressed any self-harm. So it's kind of this odd thing. They'll be reached out to and they'll be like, why are you reaching out to me? And it'll come out, that you've been tagged to being at risk. And they'll get real tough and say, well, I've not done anything. And, they're like, well, you're not done anything, but you look just like people that have tried to hurt themselves. So that's traditional prediction. It's if you can't imagine an experiment, okay, how can you tell if it's traditional prediction? If you literally cannot imagine an experiment, okay, a randomized experiment where you were sort of randomizing a treatment of some kind, okay, randomizing aspirin to somebody. If you can't think of that, it's probably prediction / description. It's very, very important, but it's probably not causal. Causal is always going to be it can be reframed as an experiment. Okay. It can be reframed as an experiment. That even if it's not going to be an experiment, the idea though, the idea of the experiment of like treatment group, control group, and varying some intervention is very, very helpful. Okay. It's very, very helpful. So causal inference is a type of prediction, but it's a prediction of a counterfactual that's associated with a particular choice. What it's going to do is it's going to use another group to try to accurately predict that missing counterfactual. Sometimes it is done in a way where it would be dishonest not to believe it, and sometimes it is a little challenging to believe it, okay? The RCT probably is a good example. When it is well designed, it is a very good example of something that just seems almost like magic. And then there are other things like, you know, subclassification weighting, where you can't help but just sort of be like, that's interesting. Let's hold that thought, and not throw it away. But that's pretty. I don't know if I'm gonna bet on it the way that I would bet on an RCT, but everything's different. So we move into the foundation of well, no, you don't necessarily, not necessarily, Ronald. In fact, synthetic control has been developed for study in countries. We'll look at some of those. Um, so you'll get to see if you think that this could be something that might be helpful. What we instead are saying, because there is no other well, we're going to see this like once the way we're going to frame potential outcomes, it does frame things as though there are these other fake earths or fake people, but it's a framing device. Okay, it's a framing device. It shouldn't be thought of as realistic. It's something though that weirdly enough maps directly into stats, but as in and of itself, it's not telling you something like string theory or anything like that there's multiple worlds. Of course, it's a free country. You can believe that, but that's not its core thing. So causal inference is a scientific field within and across pretty much all the scientific categories. All of them have a causal inference in them. And so it's focused on this idea that I've been saying, which is, it's a physical law. In some areas, it's much more emphasized that it's a physical law, like maybe in physics. But the causal inference part is a little different from the causality part. The causal inference part really is about the believing, right? And should I believe this thing? And what's evidence? Okay. So the core idea in causal inference is to distinguish between the true thing and the hypothetical thing, or what I call the realized outcome and a counterfactual, what would have been possible had something been materially different. And there's a lot of people that lay ownership to this idea of the potential outcomes. Goes back to John Stuart Mill. You can definitely see it in the moral philosopher, John Stuart Mill. You can see it in the statistician, Ronald Fisher. But the person that writes down the actual letters and then uses those letters to draw statistical deductions about causality is a young man, Jerzy Neiman, 1923, master's thesis, did not get published into English until 1990. He spent his career at Berkeley, as I understand it. I've got a biography of him on the shelf, but I haven't read it yet. But it's really, even though he did that, even though he wrote that and he worked that out, and you see these ideas of potential outcomes, it's really I think it cannot be overstated that where we are now is because of the practical, like, missionary style personality of Don Rubin, who was unbelievably prolific throughout his career. Former chair of the stats department. He's emeritus now. And he's the one that really pushed potential outcomes beyond just a single master's thesis and beyond the experimental design. began to push it into the observational design, which is where we kind of are now. So let's think about something that's going to affect person's wages. What are we going to do? Do I have an actual policy? All right. Yeah, job training program. I skipped it. So let's have a job training program. Call it college. All right. College is going to be the job training program. And it's going to be a dummy variable. And the synthetic control is going to be a dummy variable. All right. So if you have in your mind, my treatment variable is the percent of the population that is, of a particular religion in a country, well, you're not going to do synth for that. All right. So this is like an intervention. All right. It's like a one-time intervention, or it's a particular intervention. It's a dummy. All right. You're either in college or you're not in college. And it's a person, we'll do person specific. Potential outcomes refer to the outcomes. All right. So D refers to the right-hand side variable. Potential outcomes, it's as though it's referring to the left-hand side variable if you think in terms of regressions. But it's a little bit quirkier than that. Potential outcomes describe each person, and each person has, for a binary treatment, has two potential outcomes. All right, so Sebastian has two potential outcomes under this job training program. One is his wages. If we're looking at the effect of the job training program on wages, he's got a wage in a world where he got a college degree, right? We're not saying that it's causal. We're just saying, here's two things. He has a college degree and he gets a paycheck. We're not saying it's causal. We're just saying in a world where he's got a college degree, he gets paid this amount of money. It could be nothing. It could be like $1 billion, right? But they're both there. And then there is this hypothetical other situation, as Ronald said, like another world. Don't think of it as literally a world, though. Okay, it's a thought experiment. There is a situation. It's possible that Sebastian didn't go to college, right? A lot of people don't go to college. Maybe Sebastian could have not gone to college. Had he not gone to college, he'd have some wages. If they're the exact same wage, he's making $100,000 with a college degree and $100,000 without a college degree. It doesn't look like the college degree did anything, at least for his wages. Okay. And that's how the definition of the treatment effect comes about. The individual treatment effect, delta, equals the differences in the wages for Sebastian in a world where he went to college and in a world where he didn't. And I don't mean before and after. I mean right now, April 6th, 2024. April 6th, 2024 at 9:55 a.m. Central Standard Time, Texas. Sebastian has a wage. He went to college. Sebastian had a wage. He didn't go to college. Exact same point in time. Obviously, they cannot both exist. That is not the point. We are not trying to describe reality. We are trying to define the treatment effect. Elizabeth Stewart, a Don Rubin student, I interviewed her. She's at like a dean or something at Johns Hopkins. And she said, I asked her, something about treatment effects. And she said, she did her PhD at Harvard in the stats department. And she was like, the real advantage is the defining of the treatment effect. That's its strength. Its strength is in the clear definition of the treatment effect, because a lot of people outside of the potential outcomes find it hard to describe what a treatment effect is. Okay. But you'll notice here, it's like, there's no model. There's no economic model. It's just saying, here's two things, compare them, contrast it to a counterfactual. So, but the problem here is we have a missing data problem, because I bet, without even having spoken with Sebastian, I bet Sebastian has gone to college, just because I tend to draw a lot of PhD students and faculty. So I bet Sebastian has gone to college, which means Sebastian knows this one and he doesn't know that one. He doesn't know that one. He'll never know it. Because you know why he will never know it? It literally doesn't exist. It's fictional. It's like the Loch Ness Monster or a unicorn, right? We can talk about them, we can tell stories about them, but they're not real. That right there is not real. No one knows they're counterfactual. No one knows they're counterfactual, okay? No one knows any counterfactual, because they are, by definition, things that do not exist. So it's weird to say it's missing, Don Rubin always will call it a missing data problem. All right. And I think like that is helpful. It's helpful to say that things are missing data problem because we do have techniques for predicting missing data. But I like to emphasize first the philosophical, which is, yeah, it's a missing data problem. It's a missing data problem, in the way that like the dodo bird is a missing bird, versus like my cat, my cat, like, let's see, can you see this cat right here? I wonder if you can see. Whoop. This is Betty. Can you see her? Betty? There you are. Can you show people? That's not really working. Well, anyway, Betty's right there. And I had to put the big sleeping thing right there because otherwise she'll be all in my lap. Sometimes you can't find Betty. I had my friend Zach over last night and he brought his kids and they were like, "Where's Betty?" And I was like, "Well, she's here, but she's terrified of you, so you're not going to find her. She's missing, but she's here." Okay. But if he says, "Where's the dodo bird?" And I'll be like, "Well, he's dead. He died 200 years ago when somebody, so, he died 200 years ago and that's why he's gone." So here we go. There's Betty. Betty, can you say hey? Sleeping? Don't wake her up. And I got another one over here. That's Ronnie. And then I got two more. I might have a problem. I feel somehow like it's my responsibility to make sure none of the cats that I've ever known die. So, all right. So, individual treatment effect. It is a difference between Y1 and Y0. It's a difference between Y1 and Y0. And, you don't know it. So you can't measure it. So this is that warranted belief stuff, that knowledge, right? So like knowledge would be to know it, right? Like that would be like knowledge to know, like Sebastian could know the effect of college on his wages if he knew both of them, right? So you don't know your own counterfactual, so you can't know it. That means any summary of those individual treatment effects also suffer from the same problem, okay? And we're just going to focus on one summary of the individual treatment effect. It's called the average treatment effect on the treated. It's the most popular parameter. It's hard to kind of imagine like popular parameters, but it is. It's the most popular parameter. Well, that's not true. Anybody that runs randomized experiments is estimating average treatment effects. But if you're doing the quasi-experimental panel stuff, diff and diff, and synthetic control, you're estimating the average treatment on the treated. And given how popular diff and diffs are, you're probably pretty interested in this parameter. Here it is. It's the average delta here for the treatment group, which is Y1 minus Y0. These are averages over large groups of units, Y1 minus Y0 for the treatment group. And then that means that the ATT is expectation Y1 for the treatment group minus expectation Y0 for the treatment group. And it's in red because it doesn't exist, which means we cannot calculate the ATT, which means there's this humility that we have to have, which is that, if we define knowledge as knowing both of them, can't know it, but you can estimate it. That's the key. That's what causal inference is about. It's about estimating it. Which is more relevant? It depends on the question. It depends on which population you're studying. So it's like, it also oftentimes depends on the policy. So like if you're going to invent a vaccine, presumably, you want everybody to get vaccinated. That's the whole population. If it's the whole population, and every person in the population has an individual treatment effect and you average them, you're wanting to know the average treatment effect. Okay. But let's say that you're wanting to know the effect of summer school on students' grades, but you know that the only people that go to summer school are struggling students, right? You're not planning to put everybody into summer school potentially. You're just wanting to put you're just wanting to know the effect of the summer school on people that went to summer school. That's the average treatment on the treated. It's all about the question. If you wanted to consider herd immunity or spillover from treatment, well, that I'm not positive about. I'm just saying, if you are wanting the policy to be applied to everyone, okay, if your goal was everybody gets treated, that's the average treatment effect. That's what we're saying. So if you're thinking of a group that you're trying to study, you're already moving away from the average treatment effect. Like if you're wanting to know the effect of, if you're imagining a study where you're wanting everybody to go to college, that would be the average treatment effect. But if you're wanting to know the effect of majoring in English on those people who majored in English, it's the average treat on the treated. If you want to know the effect of majoring on the English and you're imagining everybody's going to major in English, it's the average treatment effect. It's it is there is no one that's more relevant, and there's no one that we should care about more. It really does. It's really the research question that drives it. It's really the research question that drives it. My point here is to say, given the popularity of the diff and diff, probably a lot of people care about the average treatment on the treated. Looking at the effect on the people that sorted into the treatment or the people that got the treatment, trying to figure out their counterfactual. And so this is what we're missing. We're missing their Y0. So everything in causal inference for the ATT anyway, it's about estimating that. It's not about estimating that. That one's perfectly fine. There's nothing wrong with that one. The ATT is the difference between this one, which is observed. For the treatment group, they're Y1. It's just the data. It's just the outcome. This is what you don't know. And so what you're doing in synthetic control is you're estimating that. You're estimating it as you are in diff and diff. And you can do that in matching also. Okay. All of these techniques, really, except for regression discontinuity design, are going to be, and IV, are going to be trying to get, they can get the average treatment on the treated. Okay. And some of them get the average treatment effect. The matching methods can get the average treatment effect. It's just the assumptions to get there are a little bit stronger. Okay. So, all right. First, what we're going to do, dig into this method called synthetic control. Tell you where it came from, then we'll watch a video of Dr. Alberto Abadi at MIT. He was a student of Josh Angrist at MIT, and he was part of that first cohort of students with Jonah Gelbeck. Esther DeFlo was also a Josh Angrist student and a colleague of Alberto Abadi. So we're going to look at his original method, and then we'll look at this demeaned method kind of briefly, and then we'll look at this augmented method. But I'm going to spend a lot of time on the original because I really want you to get that. So we start here. We're going to start here as foundation. We're going to understand it inside and out. We're going to practice with it. We're going to try to learn good practices, try to understand its bias, because its bias is what drives all these new innovations. If it wasn't biased, if there were no biases associated with it, you'd be done. Okay. Then we're going to look at two methods that try to address the bias. One is by Bruno Furman and Chris Pinto. I interviewed Chris Pinto last season on my podcast. There was an early modification they did, which was a simple demeaning to try to address the bias of synthetic control and offer the solutions. But it was a lot more about the bias. And then there's a newer work called Augmented Synthetic Control by Ben Michael Feller and Jesse Rothstein. I'm going to interview Jesse Rothstein next Friday. Further modifications of this bias, tries to address the bias in a different way, draws upon work by Abadi and Embens from 2011, which I'll try to even briefly explain that a little bit. And here's a graph showing that synthetic control has been growing. It is growing in popularity, but you got to keep an eye on this y-axis. The NBR working papers. Here it is showing up for the first time. That's almost certainly Alberto Abadi's paper that gets published in 2003, but it's fairly uncommon. I mean, I think that's one paper, then no papers in the NBR working paper series, and it pops back up. Heck, that might even be below. That could be the one, and that could be two. I can't tell. Then it goes up, and then it does begin to rise. And in 2018, about 2% of all the NBR working papers is synthetic control. And this is the top 5, and it was just, non-existent. Starting in 2010, you see some, okay? You see some synthetic controls. I get a synthetic control paper in a top 5 in 2018. There'd been a few others before. I actually did not know of these few others before. I actually, for a long time, thought ours was the first, but apparently not. Not until I saw this picture did I realize that. So the history of it comes from a paper called The Economic Costs of Conflict, a case study of the Basque Country. Basque Country is a beautiful part of northern Spain. I've not been there, but I want to go there, like a big nerd. I want to go to the Basque Country because that's where synthetic control was born, which is probably the lamest reason to go to any place, but I want to anyway. It's written by Alberto Abadi and Javier Gardezabal, published in the flagship journal in economics, American Economic Review, and I've posted it at readings. And it'll say Abadi and Gardezabal 2003. And this is what Abadi wrote me in an email like a week ago. I asked him again. I've asked him a few times, where'd you get the idea for this thing? And he says, about synthetic controls, I had played with related notions for some time, thinking about panel data methods to measure the effects of aggregate interventions. But the idea of synthetic controls shaped up in my mind with the Basque Country example. As always, taking vague concepts to data helps. There wasn't much one could do in terms of diff and diff. For the Basque example, when I saw what is now figure 1 in the Basque paper appearing on my computer screen after the code finished running for the first time, the value of the method became immediately clear. And here's what the picture was. This is GDP per capita. And it's a study of terrorism in the Basque Country. Basque is one of 2 places that has a history of terrorism. And he grew up there. And somebody told me, anybody that grew up in the Basque Country at this time probably witnessed it, witnessed some of this stuff, or maybe even knew anybody. So he's got some line here. Look at what's going on. It's some black line, some dash line. Black line is actual with terrorism, and the dash line is synthetic without terrorism. Okay. And he's got real GDP per capita in 1986, and he's got time. Okay. So he must have saw this and was like kind of stunned by it. He was like, yep, this is going to work. Something about the visual. This is kind of like, I just want to pause and say this. Something about the visual of synthetic control caused even its owner to kind of think that it had value. Right. And that's something for you to be thinking and keeping in mind. So when we get back, take a 15-minute break, we're going to listen to Alberto Abadi in his own words, share the origin of the method. All right. And again, this is me trying to kind of having a soft launch of the workshop before we just start diving into more technical material. All right. So we'll take a 15-minute break, come right back. We'll put a little music on. I'll see you guys in a minute. Resume. Here. All right, we're going to listen to Abadi. And then after we listen to Abadi, we dive in. Maybe it's a little technical. But we're going to still kind of do the slow and steady wins the race kind of approach. All right. And just a few minutes, about 5 minutes of him talking about, where this came from. The setup here, he's talking about terrorism. It says Bangladesh for some reason, but I think it means Basque Country. That's where he grew up. Okay, so we're just gonna make it as loud as I can. Hopefully you can wait. I think I can do closed captions. There you go.
And so there was kind of a long process that luckily now is over.
So it was concentrated in Basque. It was concentrated there.
Was mostly concentrated in Basque Country. Like apart from terrorism, there was extortion to some entrepreneurs and so on, like in order to finance the terrorist activities of the organization. And there was also terrorism in other parts of the country. Yeah. And most of it happens during the transition, the political transition with Spain. Until I was kind of 6 or 7, Spain was a dictatorship. It's difficult to believe that now, but it was. And, there was a long process of political transition to democracy that was very successful, but it was also very painful for many people. And, this happened as a part of that in part.
Yeah.
And in the terrorist activity.
Yeah. So I'm curious about that, both because of its history and in your life, but also it seems like it's so intimately connected with the creation of that synthetic control paper. I just am curious, how did that paper come about? I wrote down just a couple of things that it has that paper, that synthetic control model. It has so many elements from the counterfactual tradition that I sort of associate with you a lot: matching, weighting, aggregating, important treatment parameters using weights, imputation of counterfactuals, difference in differences. And you did it almost immediately after you graduated. And I was just wondering what's the story of that paper, and how did you end up doing that? What was the reason for it?
So the story of the paper, I was, as I said, there was a terrorist conflict in the Basque Country, and there was many people talking about in the newspapers and in the streets, talking about, what is the threat of terrorism on the economic prosperity in the Basque Country. And shortly after graduating, I was invited to a course in my alma mater at the undergraduate level in the University of the Basque Country. I was invited by Javier García. And while I was teaching this course, we started talking about collaborating in these projects and measuring the effect of terrorism in the Basque Country. And at the time, it was a purely empirical paper, and we were, it was a very, very personal interest in trying to measure, something that it was important for us. And the thing is that when we tried to do it, we realized that the available methods, were not going to be, appropriate in that setting because of the aggregate level of the event or intervention that we were talking about, that is terrorism conflict, and also because the Basque Country is a relatively idiosyncratic region within Spain. I mean, we couldn't think about any good match for that, and that's how it came to life. And what we realized later, is that it has many other applications in many other fields, and for many other questions, and has become popular, I think, in part because of the transparency of the methods and because of the interpretability. Yeah. But also because many of the policy interventions and events that we care about are in fact at the aggregate level, and the tools that we have for policy evaluation were constructed with the idea that we have a big sample of units, and some of the units are exposed to intervention of interest, many of them, and some are not, and we are going to compare them. And we have much less of a theory and a conceptual framework for the case in which the policy interventions are implemented at an aggregate level and affect only a few units. But the fact is that many of the policy interventions that we care about are like that. Yeah. And that's why I think that this set of methods, and including difference, synthetic controls, and so on, they are going through a, like a very popular phase because, people realize that there are like a lot of, potential, applications and implications.
Right. So in that Basque Country paper, was it, so when when I'm thinking about you guys writing that paper, was it sort of very long into the paper where the project where you started to realize you needed to construct this new estimator, or was it something you had an idea for it even before the project?
No, it was completely, inspired by the project, and it's something that happened very, very early in the process, if I remember correctly. In the same paper, we also have like like a second part of the paper in which we run an event study, try to think about the another way to measure the effect of terrorism in the Basque Country, and that took a little bit longer time. To do because of the data availability issues and how to think. Also we have to think very carefully about how to do an event study in for a case in which the effect of the treatment is not immediate, but it may happen like over a long period of time. And how to measure risk in that case.
Yeah, right. Yeah, you don't. That I have a paper like that with fracking, and we fracking had the same. Okay, so let's get back to that. So he says elsewhere, he says, and I was hoping I could find it, but I didn't find it. So, but he says elsewhere something kind of interesting, that another way the synthetic control paper was born was because he grew up in Basque Country and he loves the Basque Country. And, this issue of terrorism in the Basque Country had always been something that was very, affected him, affected his family, affected his life, affected his childhood. And, it's just, you never know. It's just something for you to be thinking about. You never know where things are going to come from. And so one thing just to remember, working on projects that you really care about, it's kind of random what takes off. It's kind of random what ends up being, impactful. But something just to kind of keep in mind is doing your best on the stuff that you love is probably a good dominant strategy as best you can. So what the heck is this thing called synthetic control that we've been talking about for an hour and a half? Well, Susan Athey and Hito Embens, they say it's the most important innovation in causal inference the last 20 years. That's pretty high praise from a John Bates Clark Award winner and a future Nobel laureate and a current Nobel laureate. So that's a pretty big deal. Originally designed for what is called the comparative case study, ongoing developments have extended it to multiple treated units, differential timing, bias adjustment methods, and even modifications to the core diff and diff model that incorporates some synthetic control in ways that I think are intuitive to a lot of applied people. Methodologically, it's one of the frontiers of the causal panel models, just like diff and diff has become one of the frontiers of the causal panel models, synth has too. And so you're seeing all these modifications all the time. You don't really see as much of it as diff and diff because the popularity, the baseline popularity of synth is like, a tenth of what diff and diff is, but still you're seeing it. And what typically happens, good or bad, what typically does happen though, is that people will move to synthetic control when they say they can't do diff and diff. You saw that actually. Did you notice Alberto Abadi said that? He said, he basically invented synthetic control because he couldn't really find a good match and he didn't really feel like diff and diff was going to work. So that's like part of its origin story. And I think that is kind of a similar thing that people will take that position. So what's a comparative case study? Comparative case studies are a single aggregate unit gets treated, another unit doesn't get treated, and you compare them. It's usually a difference in differences. The aggregate unit is a country, state, school, firm. The aggregate event affects that state, school, firm only, affects them. And there's two traditional ways that people, oh, and I want to real quick change my, back to my microphone. And there's two ways that people have studied it, qualitatively and quantitatively. Probably for most of us on the call, it's the quantitative that we're most familiar with. But if you're in political science, you know both of them. So in qualitative comparative case studies, it doesn't have any quantitative parts to it. So de Tocqueville's Democracy in America is an example of this. Started out as a study of the United States penal system, kind of evolved into a study of democracy, constantly compared back to France. It sort of started this comparative political economy. Sometimes there's not even an explicit counterfactual in these writings, or if there is, it may not be very principled, some sort of subjective research or decision. But also, there won't be any real quantitative claims. You won't hear somebody say, de Tocqueville's not going to say GDP per capita fell $500 when compared against France. But that's exactly the kind of thing that's going to be said in a quantitative study, right? Traditional quantitative studies were diff and diffs. They involved natural experiments. You had a unit, though, a single unit that gets treated. You had a group of units that weren't treated that were chosen by the researcher to function as the comparison group. David Card's oftentimes associated with it. His Card and Kruger, his minimum wage paper in 1994, could be an example of a comparative case study. New Jersey is getting a minimum wage. Who's going to be the control? How about Pennsylvania? Next door. Why Pennsylvania? It's next door. Why does that matter? That's well, you know, that's beyond the scope of the project, right? So it's like that's kind of a common thing. So these traditional quantitative comparative case studies, they're diff and diffs almost always. They just have one treated unit. Okay. And then they have an arbitrarily chosen selection of control group units. I don't want to, maybe arbitrary is not exactly the right phrase. There are reasons for why the control group is chosen, but the reasons are coming from the researcher. Okay. So there are pros to doing it. The traditional study, it's not synthetic control. The pros are that it takes advantage of policy interventions that took place at the aggregate level. That's actually what Abity said too. He said, that was the advantage of synthetic control and diff and diffs, is that oftentimes the policies are happening at an aggregate level, and you want to have tools that are appropriate for that scenario. And another good news, if there is data available, the data that is often available is the macro level data. The macro level data is in abundance. Micro is the harder one, but macro is more common. But the cons, and I've kind of alluded to it, you can't do causal inference without a control group. Who's going to be the control group? It typically is fairly ad hoc. It's not data driven. The person will choose the control group. And insofar as a researcher is choosing a control group, okay, and even in differences, you're not choosing your control group. Okay, you're using all the units as a control group. You're like investigating pre-trends to see if that's appropriate. But in these traditional comparative case study approaches, they won't use all of the units as a control group. They'll just pick a few. All right. That tends to be ad hoc, opens up researchers' biases, even if it's unconscious. And the standard errors are not really reflecting what we think they are. The standard errors are reflecting the uncertainty of the sampling variance coming from the sample. But in causal inference, usually when you're doing this kind of thing, the uncertainty of the study, it's coming actually from the estimate from the control group. Does the control group reproduce the counterfactual of interest? All right. So there's these pros and these cons. And what synthetic control tries to do is keep this, but address these things. So let's look at the 1980 Fidel Castro event that was studied by David Card in 1990. So Fidel Castro makes an announcement in 1980. He says, anybody that wants to leave Cuba can leave Cuba. They just have to leave in the fall, autumn, from the Mariel boat dock. All right. There's a fleet of boats that basically, a straight line from Mariel to Miami. The opening of the movie Scarface, which I think is it's not Jonathan Demme, but it's De Palma is the director, and it stars stars Al Pacino. It's set with the Mariel boat lift. It's a natural experiment. It raised the size of the Miami population of Cubans by 100,000 people. I mean, just kind of imagine that. Imagine on a day, 100,000 people just dropped into your city. The labor force grew by 7% with this event. It was huge. Okay. And Card wrote a paper about it. And it's probably his seventh most cited paper. It was a big controversial study. He uses it as a natural experiment, does diff and diffs to measure the effect of a sudden influx of immigrants on unemployment among less skilled natives. And his question was, well, how do flows of immigrants affect the wages and the employment of natives in local U.S. labor markets? He wants to basically know if you shift the labor supply curve in a neoclassical model with perfectly competitive labor markets and identical workers, you should see a reduction in wages of the domestic worker, at least temporarily, and a reduction in well, it depends if you'll see a reduction in employment, but you can it can happen. Okay. And it kind of depends on a bunch of production function stuff. George Borjas talks about it really well in his labor economics textbook. So Card pulls data from the individual level unemployment data from the current population survey for Miami, picks 4 cities as a control. Here's the real quick pictures of people leaving Miami on the Mariel boat lift. They're super excited. They're sorting out, they're going to live somewhere they were wanting to live. Not too far away. There's probably family waiting for them. And it's Miami. Okay. Great city. So his treatment group was low skill workers in Miami, because that's where the Cubans went. And his control group is 4 cities, and he chose them himself: Atlanta, Los Angeles, Houston, Tampa, St. Petersburg. And he's got this little section right here where he explains his reasoning. And the reasoning that he uses is good reasoning. He's using matching logic. He wants to find cities that he thinks are similar. He says, I've assembled similar data for whites, blacks, and Hispanics in 4 other cities: Atlanta, Los Angeles, Houston, Tampa, St. Petersburg. These 4 cities were selected because they had relatively large populations of blacks and Hispanics, and because they exhibited a pattern of economic growth similar to Miami. So he's basically saying, I'm matching on race and economic growth. Okay. So he does do something. He just doesn't really report anything about that, like, of all the cities in the country, is that the right way to do it? Is that the best one? Is there a way to match, like, is that the best cities or whatever, that kind of concept. So he just picks it. He does a diff and diff. Here's the way the diff and diff goes. Take 1981 minus 1987, 1979 for the 2 groups, for the 2 years, and go 1981 minus 1997 for Miami, whites. Unemployment goes down 1.2 percentage points. Do it again for the comparison cities, goes down a little bit. This comparison city negative 0.1, that's the assumed counterfactual for whites in Miami. Okay, and if it's true that in counterfactual, Miami's unemployment would have fallen from 5.1 to 5.0, then this comparison right here between those two is the estimated average treatment on the treated. It fell is the point though, that after the 100,000 Cubans arrived, 2 years later, unemployment was lower for whites than it had been. Well, it was 1.1 percentage point lower than it would have been in counterfactual, right? It would have been in counterfactual. Hold on one second. It's an aggregate level. 1023. I'm sorry, I was in the wrong thing. I'm not entirely positive. He didn't elaborate. I'm not entirely positive what he was talking about. So there's this question here, but I'm sorry, I was stuck in a different, I accidentally had clicked a different button here, Guanji, so I didn't see your question. He said, why is the aggregate part important? I'm not really sure. He says this a lot. Shows up in the JASA article too. I meant to ask him. I don't really know. Aggregate data is used with diff and diff all the time, so I'm not really sure what he meant. I should probably dig into that a little bit because it's kind of just said without a lot of explanation. Maybe somebody knows. Maybe Zakin knows. Yeah, I mean that's true. GDP is about macro level. Although the aggregation is based on production of final goods and services, which are micro. I really don't know. I really don't know. It's a great question, Guan, and I'm gonna ask. I'm gonna get into that because it's in the JASA, but it just doesn't say it. But maybe it's in there, and I'll find it. I'll try to look at that. For whatever reason, though, Abadi did not feel that the diff and diff would work. Most of the time, the reasons that I thought diff and diff wouldn't work here with one unit is that when you only have one treated unit, the standard errors are too small. And then secondly, but he discussed that. He discussed the standard error issue there. I wanted to bring this up though too. Watch what happens with the bike. So the white one, I think is kind of like interesting because the comparison cities basically don't change their employment. So the 1.2 that falls minus negative 0.1, there's a sense in which the treatment group was responsible for that number, right? Like it's a negative 1.1 and the negative 1.2 is the treatment group. But look over here. For African Americans, I don't quite know all that's going on. There is a recession that starts in the early 80s. Paul Volcker was the chair of the Federal Reserve, and he does that. It does that strong restriction on the money supply. But so I thought maybe that's what this was about, but it's not affecting the whites. So there's a lot of some macro stuff I don't really understand. But I think this is around the time of a recession. So African Americans saw their unemployment rise. And he's looking here at lower skill workers. Okay. And they rose by 1.3. Ronald, you might know. I was kind of curious if you might know. 8.3, 9.6 is a 1.3 percentage point increase in unemployment. So that's speaking to that 1.3 percentage point increase in unemployment is kind of speaking to, maybe there was nothing for whites, but it's going to be there for blacks. But when he looks at the comparison cities, the rise is even larger. 1.3 minus 2.3, negative 1. People typically find these kinds of diff and diffs a little bit dissatisfying because the control group drove that diff and diff. But there's nothing wrong with it. There's nothing wrong with it. What that's saying is that in counterfactual, yeah, Why is it hitting whites so barely, though, is what I was wondering, Ronald. I mean, I know that African Americans have higher unemployment during these recessions, and they might be specializing in area like maybe construction or something. But I still was a little puzzled that it would be isolated. I mean, that's like really low unemployment for having two recessions. It's probably worth digging into it. And maybe this is the thing, that this was these kind of diff and diffs that happen in the middle of shocks like this. It's like the diff and diffs that happen in the middle of COVID. You can still appeal to parallel trends, but you do have that headache in your mind of like, boy, COVID's just doing all kinds of stuff, and it's going to be really hard to control for it all. But he finds here a negative result. A negative result. Ron, I'm watching what you're writing. Negative result. 1.3 minus 2.3 is a -1. Basically, what this is saying is that absent the deposit of immigrants into Miami African American unemployment would have risen by 2.3, not 1.3. And so the argument is that the deposit of the immigrants is the reason why it's not that big. So it's actually results in a 1-point reduction. He found no effect on wages, but that's the other thing too. He finds no effect on wages, but it would be nice to put that into the slides. I might have this in the readings. But his analysis used diff and diff. It was a controversial paper. George Borjas, in particularly a labor economist, did not agree with it, interacted with it a lot, even relatively more recently. And he used diff and diff. His estimate's unbiased. If the control group's change in Y0 is approximately equal to the counterfactual, so that means everything's being driven by the control group. The control group delta Y is proximing for whatever that unknown delta Y is for the control group, treatment group. Okay. And he selected his controls based on, like I said, based on logic, matching logic. He looked at covariates and like trend logic, employment growth, but he didn't really report anything. He just kind of said it, but still that was there. But you see that black result, and you do have to wonder, well, I wonder if he had chosen a different comparison city. If he had chosen a comparison city that saw that -0.1. Yeah. Yeah, I bet you're right, Ronald. I think he does try to focus on lower skill workers, but I don't remember exactly what that would have been. That your point might still be the case. So here we have, what if the decline amongst African Americans had been that one, -0.1? Then you would have found a positive increase in unemployment. So there's some uncertainty in the result. Was it a no effect? That's the other thing too. The standard errors are really big. Was there a no effect? Or was it the control group? Okay. So this is where Abity and Gardezabal come in. They do this synthetic control in the AER, study of terrorist attacks and a terrorist truce in the Basque Country on GDP. It gets revisited again in 2010. I actually, to this day, still do not fully understand, what the novel contributions of the 2010 JASA are. There's definitely a lot more proofs about the bias. And it's clearly like only about the synthetic control, but it was written with two political scientists and who were PhD students at Harvard, who have gone on to successful careers. And the basic idea, and at that time, that's where Abity taught at the Harvard Kennedy School. He's a phenomenal teacher. He's incredible. I've been fortunate for him to teach me at the Northwestern workshop on causal inference, and I just thought he was one of the best professors I'd ever heard speak. So I heard stories of them clapping for him at Harvard Kennedy School. So the basic idea is to use a combination of comparison cities, units as a counterfactual. Here it's not cities, it's like the 16 kingdoms or whatever, 12 or 16 kingdoms of Spain as a counterfactual for a treated unit when the units are chosen. This is your goal in synthetic control. All right. It's a hands-off approach. All right. You're not going to be picking. You're not going to be picking your controls. You are going to be picking covariates and things of that nature, but you're not going to be picking you're not going to be picking the cities or the states. So synthetic control is a constrained minimization problem where the target goal, the goal of the method, the goal of the method is not really to estimate a treatment effect. The goal of the method is to minimize a vector of squared gaps or matching discrepancies in the pre-treatment characteristics. This is precisely something that Abity and Embens worked on in the 2000s. There's a 1999 giant NBER working paper between Embens and Abity that gets peeled off into 2 econometricas and 1 Journal of Business and Statistics. I wish my 2 long of papers could get peeled off into 2 econometricas in a top field. Usually my 2 long of papers just don't get published because they're not any good, but theirs was good. So synthetic control is a constrained minimization problem. We're going to look at what I mean by that in a spreadsheet in just a moment. And you can see what it's going to be is a minimization of a vector of squared gaps in the pre-treatment characteristics. And you're going to choose weights. These weights that you're going to choose, they're endogenous weights. This is a key part of the method. They're going to be constant over time. They're going to be there for every control group unit. They don't change over time, and they're going to be non-negative weights. And this is what people are going to mean when they say it's a convex combination of the control group units. It's going to be a positively weighted, or it's going to be a non-negatively weighted group of comparison units. That's going to be your synthetic control. So our goal, reproduce the counterfactual, but say here's our goal. So our goal is once we fab those weights, we want to reproduce the counterfactual of a treated unit over a stretch of time before the intervention. So we're going to basically match. It's a lot like matching. We're going to match in the pre-treatment period, and then we're going to check with our matching how much does it look like our treated unit over a long stretch of time, okay? And you're using covariates that are highly predictive of the outcome of interest. We're going to elaborate on that in a minute, but that's the thing you're wanting. Is this covariate highly predictive of the outcome, particularly predictive of the counterfactual outcome, okay? Not just anything. So then, so what the method's going to do is it's going to get a weighted average of all those countries, and as a result, it's going to weight their outcomes. And then we're going to follow them over time in the post-treatment period when we did not do any estimation. But that weighted average, those weights, the vector of the weights is themselves the synthetic control. Okay. Yeah. All right. So here's the notation. Oh, here we go. So the advantages, synthetic, the convex hull is an advantage here. To some, it's a disadvantage, but definitely Abity sees it as crucial. It means that the synthetic control is going to be a non-negatively weighted average of donor pool units that on average are closely resemble the treatment group. What does that mean? Okay. What that means is you're finding observationally equivalent. Your control group, quote, looks like your treatment group. That's what the positive weights or the non-negative weights are doing. Okay. So it's like, you're basically getting people that are in the vicinity of the treatment group. They're not too far away. Okay. And the convex hull is just going to be representing that weighted average. All right. The constraints on the model are that you cannot use non-negative weights, or sorry, the constraints on the model is that you can't use negative weights. If you could use negative weights, you can always get a better fit. That's why it's a constraint. It's a constraint precisely because it's not letting you optimize. The negative weighting would actually be optimal, but he does not want to use negative weights because what negative weighting will do in this context is it'll extrapolate beyond the support of the data and basically be very dependent on some sort of, functional form. So it's got lots of these, it's very closely like that approach, allowing for negative weights. That's much more in line with what a regression would do. A regression will allow for negative weights because the negative weighting is what allows the regression to have the minimum, prediction gap. But it's not going to do it. It's not going to do it because he's basically saying, look, I'm trying to model this Basque country. And, he said it's a very idiosyncratic country. I want it to look like the Basque country. Okay. So we're going to have J units, and then we're going to have one treated unit. Unit 1 is going to get treated at T0 and then going to be remain treated. Treatment does not turn on and off. Turns on, stays on. The J units are untreated. They're never treated. They're never treated units. So you have to drop anybody that's going to get treated. They're called the donor pool. So Y0 is the outcome that would be observed for the treated unit at time T, in the absence of the intervention. And Y1 is the outcome that will be observed for the same unit at the same point in time if they were exposed to the intervention. So it's just the individual treatment effect. It's just that the individual here is an aggregate unit. It's a state, it's a country, etc. Okay. So we're estimating this like an event study. We're estimating Y1 minus Y0. 1 is the treatment group, 1 is the treatment group, and T is time. And since we observe Y1 for the treatment group, we can just drop it, but we never observe that one. All right. We never observed that one. So what are we going to do? We're going to get our Y0 is going to be a weighted average of all the other comparison units. We're going to be imputing Y0 using optimally weighted control group units. All right. So here's this empty vector right here, W, that goes from W2 to WJ plus 1. All right. He puts a constraint on it. Weights cannot be negative. All right. Second constraint, they have to sum to 1. So that's going to give it that convex combination. All right. So they could all be equal to J. It could be like, 1 over J could be the weight. Or you could have 2 units, each have 1/2 weight, and everybody else be 0. He's like, it could be anything. There's an infinite number of them. Since the weights are continuous, there's literally an infinite number of these things. So X is going to be a vector of pre-intervention characteristics. X is not going to be a covariate, okay? It's going to be pre-intervention numbers for that treated unit. And then we're going to do the same pre-intervention characteristics for the control group. And then we're going to minimize that norm, right? Subject to our weight constraints, and it's going to have a unique solution. And that's going to be the optimal weights. So they consider this expression right here. And there's going to be sandwiched between these two distance measures here. They're minimizing these distance measures. In between it is this matrix. It's K by K. So it's the width and it's the height of the number of covariate characteristics that you've chosen. And the diagonal is going to have stuff on it. Okay. It's going to have stuff on it. But it's symmetric and it's positive semi-definite. So it's a lot like nearest neighbor matching. It's a lot like nearest neighbor matching, in a sense, because this is going to be this right here is like the calculation of a particular number, and we're going to be choosing W that basically makes the sum of the squared matching discrepancies to be as small as possible. But there's going to be this V term in here, and this V term, it goes by different names, but one of them is, people call it the importance matrix. All that it is it's measuring how important is that particular variable, in the minimization process. So I'm going to take a 15-minute break. Okay. I'm going to take a 15-minute break. And when we come back, we'll go through some exercises. Okay. I'm going to still a little slow, but we'll come back in just a minute. Oh, old age stuff is for the birds. Okay. All right. So let's dig into this. So this is the goal. I've mentioned all these goals. And Eduardo says there's two types of weights for variables and comparison units. Exactly. Eduardo, that's a very succinct way of putting it. So these are the weights for the comparison units. All right. They have to be non-negative, sum to one, two constraints. And we're going to solve for this. It solves a minimization problem. And then we're going to choose these X characteristics. This is the minimization problem. Minimize the square root of this form, where there is another set of weights, as Eduardo said, V. I'm just going to throw up here a little bit. It's so abstract. I'm going to show you the differences between this nearest neighbor matching when you have multiple units, and the kind of what synthetic control is going to do with this worksheet I have, where you are minimizing the Euclidean distance. Okay, so this is not what it's doing, but I still find this very helpful. All right, because what nearest neighbor matching is doing is we have multiple treated units. We've got multiple treated units. Hold on. Okay, we got multiple treated units. In this case, 10. All right, 10 treated units. They go to college, job training program. And we've got 20 comparison units, non-random selection into the program, but we've got two covariates that the selection is only based on two covariates, their age and their GPA. It's in two dimensions. All right. So we're going to have to find 10 units to function as the counterfactual for the trainee sample. There's 185,000 ways that we could do this. And here's a one random one. All right, I can just take unit 4, make him the counterfactual for unit 1. I take unit 20, do that one, and calculate the sample mean earnings for the treatment group, and then subtract out the sample mean earnings for this comparison group. And when you do that, that's your sample estimate of the average treatment on the treated. All right. You can do that. There's 185,000 sample average treatment on the treated estimates. There's only one true average treatment on the treated. Okay. When you're using matching, nearest neighbor matching, it's really similar. It's very similar to what we're going to do here. Okay. Notice how with synthetic control, what you take is you take a pre-treatment characteristic of the treated unit. So that'd be like this thing, okay? And you take a weighted average of all of the units, take a weighted average of all the units, and you sort of impute it to that, and you square it. Well, in nearest neighbor matching, you don't take a weighted average of everybody else. You just assign a single unit to every treated unit, but the rest of it, you do the same, right? So here it's going to be a matching discrepancy. That's what you can call it, right? It says like we don't get, an exact match. And you're not going to get exact matches pretty much ever. And can get this inexact match here. We're going to square it, then we're going to sum it, right? So look at this. Here's the nearest neighbor matching. Took 18 minus 39, squared it so that anything negative would become positive, and then summed it. Now, there is not a nearest neighbor matching this thing, okay? But they all kind of have similar reasons for doing what synthetic control is going to be doing, all right? So here they're going to, and I'll explain how there's like a similar kind of problem in here, all right? So you add them all together, all of the matching discrepancy squared. That's a 2093. There it is right there. You take the square root, and that is called the Euclidean distance, 45.75. Now, notice what it did. The Euclidean distance here basically treated each of the, matching discrepancies, the units here, like that's 441 age squared. But that's not 0.23 ages squared, right? The units are different, but it nevertheless added together different things in order to get to this kind of distance measure, which doesn't make a lot of sense, but that's what it does. Okay. So we did that. We did another random match, added stuff together, a different one. You get a 158, take the square root, 32.5. So you don't end up taking the square root again. It's, it doesn't really do anything. It's not really like important, honestly, even to take the square root, but it does done. And you can go through all of them. So here's the optimal match. It's this one, okay? And it matched on age first, because that's the easiest one to match on. And then you add all those together, you get an 8.9. You take the square root, you get a 3, okay? All right, so what is it going to do? What is it going to do? Well, it's not a sign. We only have one treated unit, so it's kind of like, like as though that doesn't even exist. Whoops. It's like as though that doesn't even exist itself. And instead of like finding just a single one, you're like taking a weighted average over all of these and imputing it right there, right? That's kind of the equivalent of what it's doing. But what it's going to do is, inside this, inside this, if that's the right way to say it, inside this, like this matrix differencing, where here's the W, and that's the control group units times the W, where the W is a vector, not a matrix, that is non-negative and bounded and summing to 1 for every single control group unit. You're minimizing this, but if you have multiple control group units, then, there is this like diagonal, there's this matrix that's K by K here, and along the diagonal is a bunch of 1s. And if all along the 1s, it's basically what it's doing is it's treating each covariate the same, which is, I don't know, metaphorically, I guess, similar to like treating age and GPA the same. So in nearest neighbor matching, there'll be all these like modifications of the basic idea where you'll introduce a different distance measure that's like robust to different scales. Mahalanobis distance being the main one. So, well, what are we going to do? We're not going to have the Mahalanobis distance. We're going to put in this V matrix, and we're going to not necessarily have the V matrix be, well, equal for all the units, treating all of the X's the same. Okay. We're going to allow the V matrix to be optimally chosen, because remember, we have 2 constraints. Here's one constraint, that the weights are non-negative, and then we have a second one that the weights sum to 1. So we're going to take its optimization, constrained optimization, minimize this function here, subject to 2 weights, 2 constraints. These sum to 0. Sorry, these are non-negative, and these sum to 1. In synthetic diff and diff, um, in synthetic diff and diff, I'd have to go back and check. Synthetic diff and diff does. I'm not that. I don't quite remember. It's in my notes, but I don't remember exactly how that goes. It might be. I mean, I don't think it's exactly the same formula. I don't think so, but I could be wrong because it's like doing multiple. It's doing two weights. It's doing a weight in time and a weight to find this multiple one. I don't remember how it's doing it. Constraints applied to both type of weights. Well, the constraint is applied to W. And then we've got two constraints and two choice variables. And so we can pick how we want the V to be here, but they are crucial, is the point. They are crucial. Given a set of weights, given a set of V weights, and given a set of W weights, I thought that too, Caesar, but I'm pretty sure that we don't have. Maybe I'll check in the JASA. Empirically, the V's do seem to sum to one. And they also seem to be non-negative, but when you ask that question, I don't remember in the JASA it actually writing down constraints on the V's. But I need to check. We can check in a little bit at the lunch break. That's what I've always thought too, because we'll look at it and it does appear. I've always been curious, but I need to check. So I'll check and see if I don't say it, Caesar, we'll look back and see if in fact it is putting constraints on that. But I believe that the constraints really are on just these W's, but they do seem to sum to one empirically. So I'll need to check. So here we have all possible weights that we could have. And we have all possible weights, and there is a unique solution. There is a single weight. It is called the optimal weight that will minimize that function, right? That sum. All it is a matching discrepancy too. It's just the sum of all matching discrepancies over all the x's. So here I only have two x's. I only have two, age and GPA. So it would just be like two. It could be 2. It could be 7. It could be 10, whatever. It could be whatever. But you sum them, square them, and sum them, where the V is multiplied by each of those x's, thus weighting up or down those particular x's in that final number. And it's going to be a number it'd be more like that number, right? And you're trying to get it as low as possible. And so you can see like this one right here, watch, like here. Imagine just this person's also 30 years old. I make one little change and it's no longer the men. Might look pretty close. It's the same kind of idea. So it will be the optimal match but optimal is with respect to a particular objective function. And the objective function is minimize this. That's the objective function. And so therefore it will do it by choosing W. And we are going to choose V, okay? And the V star weights directly shape W. You know what, Caesar, actually, it's a different objective function. It's a different objective function altogether to get the V weights. It's not coming from this formula. The V weights are basically given a set of V weights, you minimize it. You have lots of options for getting the V matrix. You could assess the predictive power of the covariates using regressions. Now I kind of remember. So it's like you could assess it that way. Like you could run a regression of Y in the pretreatment period where everything is a Y0 onto a bunch of covariates, and anything that's like big, you could just sort of pull those in and say, well, I'm going to let those regression coefficients be along the diagonal, right? Maybe you normalize them to sum to one. Maybe there is some value to doing that. You could subjectively assess the predictive power. Okay, you could just basically say all of them are going to be treated the same. And that would be like maybe a diagonal of ones, okay? The identity matrix. Or you could do something like this. You could say, choose V such that the W that is assigned with V. So like this, any of the numbers right here, they're endogenously based on that V. They're endogenously based on that V. Okay. So you pick any V, we'll give you a different number. We'll give you a different weight. Okay. So like I say here, therefore the V weights directly shape the W. So then you could think to yourself, well, if I have complete control over the V's, what do I think the V should be? And the way that what you want the V to be is you want the V weight to be associated with the best fit of the data that minimizes the mean squared prediction error, all right, for the pre-treatment period. And that is the default in the software, all right? So you can try to imagine like all the different V's that you could have and all the different W's associated with that V. So you pick a diagonal of ones, you're going to get a W. And that W will be right there. You pick a different V, it's like all of it changes, but the solution will still be right there. Okay, for any given value of V. So what I don't know if it's they say that it's recommended, but they, what they do is, I mean, you can hack the code and change it yourself, but your goal is to minimize. I mean, there's a good argument for this one, and that would be this. Notice these are at Y's. The objective function was to minimize the X's, but then this would be mean squared prediction error on the outcomes. This is more of a matching discrepancy kind of concept, okay? Not prediction error, okay? So they're saying choose V such that the W that goes with it is the minimization of the mean squared prediction error, and you get a unique solution. Abity recommends a lot of this is if you ever have worked with any synthetic control, okay, I got a couple of chats here. Okay, good, you found it. Abity recommends cross-validation for selecting the covariates. I've never done it that way, but he recommends that. I've always found it to be not terribly intuitive, but divide the pre-treatment period into an initial training period and then a subsequent validation period. And then for any given V, calculate the W star in the training period, minimize the mean squared prediction error of that W in the validation period. And then go about choosing it that way. Where the literature has moved is not necessarily in that direction. Though they've not necessarily moved in that direction. So let me sort of give you an example of where it has moved. All right. Well, let me show you the classic smoking paper. All right. So this is in the 2010 JASA. This is the paper that they used, not the terrorism paper, but the JASA paper. They used it to kind of illustrate this proposal. And it works really well. The W associated with each V. Well, the W, like all of these are W's associated with a fixed V. Okay, they're all associated with it, but there is one that yields the smallest number. That's a single number. W is a vector, yes. W is a vector on all the control group units. It can be a 0. You're solving for W associated with a V. And there is a single W for every V. There is a single W that will minimize the sum of the squared matching discrepancy. Big W is the vector. Here, it's the name of the vector. And then the little w's are each of the individual weights. So there are J weights. There are J total weights, and they go from W2 to J plus 1. We don't put a weight on the treatment unit. Treatment unit is called 1, so it doesn't do that one, but there are J weights, and they're fractions. Well, they're bounded at 0, and they go to 1. They're not gonna be 1. So there'll at least be 2 units that will be the nearest neighbor. Okay. So it would look like this, Sebastian. It'll be like, so it'll be like states. And then you have your W weight, W. Okay. And we'll call it like over here, it would be like, be like W1, W2. No, sorry, W2, W1, right? And then it'll be like the states like Alabama, Arkansas, right? Dot, 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 Wisconsin. And it'll be like, or Wyoming. And this will be like W51. Okay. And that'll be like the W weight. And then like here would be like the actual weight, the actual weight. It'll be like 0, 0.1, dot, 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 0. 0.3. But if you summed C2 to C5, it would equal 1.0. Does that make sense, Sebastian? So like the W is the label, the column label. And then the individuals are the weights, and they don't change over time. So the V's are gonna be like when these are calculated, okay, when these are calculated, the formula is right here. This is what's being summed. All right. And there are literally, for any given value of V, there are as many weights. I mean, it's like a giant number of weights. Well, I guess it is. The vertical axis is the matching discrepancy squared. That's right. It's the matching discrepancy squared. But think of it like this, okay? All right, so like the matching discrepancy squared, here's one with nearest neighbor matching. That's the matching discrepancy squared. Yes, exactly. Associated with some W. So like you could have had this one. Could have actual, you could like, weight 1, weight, weight prime. You could have weight prime prime. Be like, oops, be like 0.25, 0.25, 0. And also sums to 1. You could have weight 3, weight prime prime prime. And it could be like 0.5, 0.5, 0, 1.0. There's literally just so many different ways that it could be done. And what the algorithm is going to do is it's going to find the optimal one. And that, what does it mean to be optimal? It means that the basically what it's going to mean is it's like, summation. Here's the summation V x1 minus x0 W squared is a number. And when you min it, choosing W and V, it'll be the smallest number. It'll be that one. That'll be the smallest number. So it's like everything else could be like, it's like this could be like a number of like all these numbers could be like 500, like 400, and this one could be like 35. It could be like 35. And it's simply not possible to get below a 35. Every other value of W, even the smallest W, even the smallest change, will give you a slightly larger number, given this exogenously chosen V. Given this exogenously chosen V. So Abity kind of gives you guidance. He gives you guidance. He says, there's a few things you could do. You're trying to predict which of the covariates predict the missing counterfactuals, you could run a regression in the pre-treatment period on Y zeros. You could even do it in the post-treatment period with the control group. Anywhere you find Y zeros, regress Y zeros onto a bunch of covariates. Any of the ones that are highly predictive, use those X's. If some of them have big coefficients, use those big coefficients in the V. That's one thing you could do. I've never seen anybody do that, but you could do that. You could say, no, race really matters. I'm going to make race a 1. I don't think this other stuff matters very much. I'm going to make it a 0. You could but see, that kind of defeats the whole purpose. That defeats the whole purpose. Like you're now putting all your subjectivity back into it. You're just choosing this weird thing. Or you could let it be more data-driven. And the data-driven approach is that choose the value of V such that the W with it minimizes mean squared prediction error. See, this is not mean squared prediction error. This is the matching discrepancy because it's solely based on the X's. It's solely based on the X's. Okay? It's real subtle details. Real subtle details. We'll see some output from it, though. We'll see some output, and we'll talk about it. So here's their empirical application, and we're going to look at a few empirical applications. Nothing is as much in detail as this one. I guess we'll do 4 applications. So in 1988, California passed a tobacco control program, raised taxes on cigarettes, banned some kinds of forms of advertising, banned like clean air ordinances in like bars and stuff like that. But it raised a ton of money, $100 million a year, anti-tobacco projects, and that money got funneled back into anti-smoking media campaigns. So this is what they pick, this is what they pick to illustrate their model, right? Now, you cannot have in synthetic control, you cannot have a treated unit. There is not a rule. There is not a rule. There is not. No. There are some heuristic rules for the number of covariates. That part we are going to look at, but there is not a rule. But the source of the bias decreases with the number of pretreatment periods. That is true. Okay. So we're going to kind of get into that when we look at the bias, but it's sort of a vague number of periods. The central limit theorem parts of this. Usually the central limit theorem is going where we assume the number of units grow to infinity. Here it's going to go with respect to time. Assume that the number of pretreatment time series goes to infinity. And we're going to show why that's needed. Okay. So in 1988, California does this, right? We cannot have treated units as a control. So you have to drop them. And again, that's just like indifference and differences. You need Y zeros. See, if you go back, just kind of go back to the beginning here for the definition of the ATT. Here, that's what you're missing for the ATT. So if that's what you're missing for the ATT, you got to find Y zeros. You got to find Y zeros. Abity does have some rules. If you can exclude anything, if you can exclude any for good reasons, then you should. It can lead to overfitting if you do have units that are unnecessary, but we can maybe after the lunch break, I can sort of just give you a quote on that, but he does recommend dropping any units that you think ex ante really do not belong. But it's not a number. It's not really a number. It's more like, if you really do think that these units do not belong, you should drop them. All right. So here's a time series plot, 2 units, California cigarette smoking, per capita cigarette sales impacts, and from 1970 to 2000, 30-year period of time in the United States. How many pre-treatment years did he use? He went from 88 to 70. So he used 18 years. Okay. You probably should say 18 appears to be enough, since that's what he uses, although that might not be true. But he's got here California, and then he's got everybody else excluding California, right, as his control. When he goes through and solves for this optimal weight, okay, when he goes through and solves for this optimal weight, such that when multiplied by that X, the weight that gets multiplied by that X, all right, and it's one weight, it's getting multiplied by each X. It's over and over and over again, squared, multiplied by that V. So the V does change something, but when you get that optimal weight on the X's, you then apply those weights to the Y's. Then you plot it. And this is kind of what you're hoping to God will happen. You're hoping that when you fit this model in the pre-treatment period using those X's, pre-treatment characteristics, you are hoping that you get a fit that is of this high quality. Now, I'll say more about it in a minute, but when you say control group size, Joy, what do you mean control group size? Like by the size of the state? Like population size? Oh, okay, sorry, 1141. Okay. So here's the weights. Notice the dashes are the ones he dropped, just so you can tell. He drops Alaska and Arizona and Florida. So Alaska, Arizona, Florida have been dropped. The control group has to be never treated. Cannot be treated. That's why he drops these. Cannot use, Pedro Santana says it is always a sin to use an already treated group as a control. You can't do it. The already treated group does not have any information for us because we need Y zeros. We need untreated units because we're trying to take those untreated units and impute the treatment group's untreated state of the world. But yeah, if we're using Y1s, it doesn't help us. We can't use that. So they got to be Y zeros, which that can limit your sample, but not, oh, I've got so much, this cat hair is killing me. State the weights. Here they are. State weights. We dropped those guys and we've got Alabama. Notice some of these weights are getting zeros. There's a lot of sparseness in this model, in this. And the reason why there's sparseness, okay, is because we put that the weights cannot be negative. A bunch of these weights want to be negative. It would be optimal if your job was simply to minimize the fit. No, you're not gonna be able to use the not yet treated. I'll explain why in just a second, Liga. The not yet treated is gonna end up being treated in the post-treatment period. And you need that post-treatment period to be consistently an untreated, because see, this right here is your treatment effect parameter. It's your treated unit minus some weighted average of Y zeros in the post-treated period. You're needing them to remain Y zero. So for the full sample, they've got to be untreated. They got to be untreated. Okay, so here's the weights. You can add them up. It'll be approximately 1. Let's just do it. Sometimes it won't be exactly because of some rounding that's being done. but there it was. So that summed to 1, okay, which was mechanical, because we required it. Remember, we required it. So the reason why it's sparse, like I was saying, is that it actually is optimal. You know, just like any constrained optimization problem, if you removed the constraints, you would choose a different value. If you removed these constraints and you allowed them to be negative, you would get a better fit on those matching discrepancies. But it comes at a price. All right. And I'll elaborate more on that when we do augmented synthetic control. For now, just know he doesn't let you do it. He believes pretty strongly in it too. I remember in the interview I did with him, and I wish I had pulled that up. I asked him, I said, sometimes it seems, you say you shouldn't use negative weights, and it's almost like it sounds like it's unethical. Are you saying it's unethical to use negative weights? And he laughed. He said, it's not unethical to use negative weights, not at all. And then he kind of went on and he said, but you shouldn't do it. And I was thinking in my mind, I was like, well, that's ethical. You're telling me I shouldn't do it. And, it's not actually, it's normative. So he says he in his opinion, it's not. The reason why he says don't use the negative weights is that you have to have a lot of confidence over the model that's kind of generating the projection, because it's imputing off the negative weights. Here it's just using, it's kind of very non-parametric. It's just using the weighted average of the nearest neighbor and just checking to see if it's comparable to the treated unit over a long stretch. Here's the 7 things that were used. Now, it's actually not true that he was using 7 covariates. He's using 7 pre-treatment characteristics. He's actually only using 5 covariates. He's using log GDP, age 15 to 24, retail price, beer consumption per capita, and cigarette sales per capita. What he's done, though, is he's using specific values of each of these. Okay, so he's using the average log GDP per capita in the pre-treatment period, the average percent age 15 to 24, the average retail price, the average beer consumption, the exact number of cigarette sales per capita, 1988, 1980, 1975. Now, the reason why these are important is because look at what the outcome is. Per capita cigarette sales in packs. He's using lagged outcomes for the matching discrepancy. His reasoning is, I need to shave because I got all this cat hair. His reasoning is that the best predictor of the future is the past. So if you're going to find a set of weights that minimize on cigarette sales per capita in 1988, 1980, and 1975, like so here, and here, just that prior to treatment, his reasoning is if it fits really well here, those are probably going to continue to do well. That's the logic. And so he highly recommends including outcomes, lagged outcomes as your controls. Other than that, the article is just kind of filled with this, like, elderly statesman advice as opposed to a lot of, clear proofs. Then once you have this right here, once you have this synthetic control, he recommends making an event study. And the event study is the gap. It's the prediction gap. Okay, because this is a Y and that's a predicted Y. And he says, make a gap. Now, the equation for this event study is different than the equation for a diff and diff event study, but it is nevertheless pretty similar. It could, Maria, it can be anything. It can be anything. My point is literally only to say, without making any specific other statements like that, it is the average. It is the average. You could say, pick it for a particular year. You could average multiple years. You can, the point is just to say, that you are in your in this right here, okay, this is all I'm trying to say, that is a specific number. So like right here, log GDP, that's 1008. Okay, that's 1008. Every weight has associated with a number. Okay, squared, summed, that's where you get somewhere on here. All right. And so it chooses the W associated with, it chooses the W that minimizes, but you're the one that chose the pretreatment characteristics. You chose it. There's a sense in which, like, the method is always trying to remove the researcher choice, but if you're choosing the pretreatment characteristics, then you're reintroducing researcher bias into it. Exactly. Charles, he provides no guidance. He provides no guidance. So subsequent papers have provided more guidance, and we're going to look at that. That's where we're going. I'm kind of telling the story in history, the historical flow of it, but Charles is exactly right. There is no guidance in the 2010 JASA about how to choose the X's or to choose the pretreatment characteristics. So early papers were all over the place, including mine. Okay. So he says, make an event study. And here's the event study. And I think that, probably everybody on the call can read this event study pretty easily. What are they saying? Well, pre-treatment looks pretty similar. Synthetic control for 18 years looks just like the real group. The real synthetic California, except for right there, looks pretty similar. Post-treatment, it falls. Now that could be prediction error. I mean, or, actually it is prediction error. That's like, by definition, it is prediction error, but it's got a causal interpretation also, which is that each distance, each point rather, each point is an average treatment on the treated. It is very similar to the group time average treatment on the treated interpretation in that Callaway and Santana estimator. Okay, so it's just that there's one group. So it's like basically saying that right there is the causal effect in year 2. That would be the year of treatment. Year 2, year 3, year 4, year 5, year 6, 7, 8, 9. And if you took an average of it, it will be German. And actually that is exactly where people go, is using only the lag values of Y. You're correctly predicting, Charles and everyone. Oh yeah. Hold on, Ann, I'll get it. Um, what does that say? Oh, would it be credible? So that's where it goes. That's where things kind of go. And that kind of connects also with Charles, And when we were writing our paper, that was where it was always with us too. I mean, it was like, until you wrote one of these papers, you never really realized how the original paper had promised to remove all subjective researcher bias until you wrote the paper and you were like, well, I still got to choose these 7 things. So the ways that I did it in our original papers, what we were always trying to do was, I was looking at this and I was like, well, I'm going to choose I'm going to try to get it to look right. I'm going to try to make it look right. Try to get the fit as good as possible. But the literature has moved in a slightly different direction in terms of advice. Now, when you do this, all right, all you get is a vector of weights. You don't get a standard error. So how do you do inference originally in the synthetic control? You do randomization inference. Randomization inference. And what randomization inference is you take your model which is right here, 7 right here. But instead of telling R or Stata or Python that California was the treatment group, you say it was Alabama. You rerun it again. When you rerun it again, you get for Alabama a optimal W. You then use that optimal W to plot out a synthetic Alabama, okay? And then what you do with that is you construct your test statistic, okay? Your test statistic is going to be, usually your test statistic in randomization inference is the estimated treatment effect. But what Abity is wanting to do here is he's wanting to adjust. You don't remove California. You don't remove California. It's supposed to always be put back in. So what you're gonna do here is you're gonna calculate the average size of the treatment effect. I mean, it's literally the root mean squared prediction error in the post-treatment period. So you're gonna calculate that average. You're gonna calculate each of these numbers squared, sum them together, take the average, take the square root. So it's just like a sum of squared residuals kind of concept, but it's the root mean squared prediction error, right? And it's not truly a residual because it's a treatment effect, but you're getting the prediction error in the post-treatment period. And for every other state except for California, it should not have a treatment effect interpretation. For California, it's got a treatment effect interpretation, but none of the other states had Proposition 99. So their graphs should always just be prediction error. Okay. So what you're going to do is you're going to calculate for all of the remaining states, all W's for the remaining states, plotted, calculate a root mean squared prediction error in the post denominated by the pre, and you're going to plot it. You're going to plot it one way. And the reason why you're doing that, the reason why you're calculating the size of the treatment effect in the post and then like deflating it by the pre is because of because it's actually because you imposed those non-negative weights. Because you imposed those non-negative weights, you'll always end up with these outliers. All right. You'll always end up with these outliers. Because imagine you were doing a study. Imagine you were doing a study on, Messi, the football player, right? Great, arguably one of the greatest soccer players of all time. And you're like doing a study on him, and you're wanting to find. You're saying I got to use non-negative weights to create a synthetic Messi, right? It doesn't matter who you're putting in there, are potentially, for every great athlete, for every greatest athlete, this will be true. There is no way to get a weighted average of Messi using non-negative weights because the best non-negatively weighted average of all the other players will still look really, really different than Messi. This is some kind of synthetic Messi right here, and that's some kind of synthetic Messi, okay? And so what you have is that like, you've got like these huge treatment effects, but they're probably not true treatment. They're just coming from they're coming from the fact that you mechanically just cannot get a good estimate for outliers. So he recommends dropping them. So he's like, drop anybody whose mean squared prediction error is less than 20 times this in the pre-period to your treatment group, 5 times, 2 times, make a histogram of that ratio, and calculate a p-value off of the absolute value of it. And the ratio would be, I think there's 38 states in the donor pool plus California. California's rank, it's not a rank statistic the way that you think of like the KS stuff, but it's like its rank in that distribution of root mean square prediction error of root mean square prediction error for all placebos plus California is number one. It has the largest ratio, meaning its post-treatment root mean square prediction error, which is like an approximation. It's like approximately the ATT because it's just a weighted average over all those individual treatment effects. Its post-treatment root mean square prediction error is, it looks like here, 130 times larger than the root mean square prediction error in the pre-period. And no one else comes close. You know, the closest is second place, and that is someone with a 90 times larger than pre. So it's called an exact p-value. You can calculate an exact p-value from this, and it's 1 over 39 equals 0.025. 0.025. It's extreme. It's not interpreted. The p-value is not interpreted in the same way that p-values are historically interpreted. So it's called an exact p-value. It goes back to Fisher, 1935, lady tasting tea experiment. Basically means you could get a number that big randomly, and you would get it, 2.5% of the time. If there was no treatment effect, for the second one, the exact p-value for the second place is 2 over 39, 2 over 39, 0.051, 0.051. They all have p-values. They all have p-values. Usually what you're wanting, I mean, so, you do this with random noise, everybody's going to get a p-value. Someone is going to be first. The argument here is that, under the sharp null, that there is no treatment effect, California would have one this large 2.5% of the time with probability 0.025, that it would have the largest. And that's how you interpret it. And you could say, and then all the way down the line, this one right here had no treatment effect. And that's where it showed up in the distribution of the null. There will always be a distribution of the null. And you would have a p-value associated with it. Okay. All right. So we're going to pause there, take our lunch break, come back 5 minutes on the hour. We're going to do an exercise together. And I'm going to illustrate for you a way to do it in Stata. And I'm going to try to do it. I'm going to get it in R also. And there is a way to do it in Python, and I'm just going to kind of Google and find it, but I'm not going to be able to do it live in Python. I believe that it's on the book, though, and you'll be able to see it. But we'll come back in 1 hour. We're going to do a coding exercise together. And hopefully in the coding exercise, you'll see in the coding exercise the logic of everything we did, how to interpret it, all those things. Okay. So we'll come right back. All right. Come right back in a minute. Open this up. It's a tunnel. We're going to keep it in here unless it is insane. Let's see what happens. See if this thing does. Ooh. Wait, how's it doing? All right. Come here, guys. All right, here we go. Oh, you can do it. Do a little thing. Yeah, maybe I'll do that. All right, we're gonna do it. Now we're gonna do it. We're gonna do it. Ronnie, come here. Look. Come in there. Yeah, there you go. All right, let's see if these kitties like it. Okay. All right. So, here we go. Okay. Yeah, so German's like, isn't the logic the same? Yeah, I mean, but that's the way this p-value is computed, is that it's entirely possible. Okay, so it is entirely possible that this right here is a product of chance. Okay, it would occur. Uh, it is how would you say it? It is entirely possible that this is a product of chance. The p-value associated with it being a product of chance is 1 out of 39. The p-value associated with this one being a product of chance is 2 out of 39. So yeah, like you could do that, but that is how the exact p-value calculation occurs, is that there could be a false positive. You could be finding something. But that's the Fisher-Sharp null, and that's what was proposed. That's how these are used, is that here we know there is a treatment that occurred. Okay, this is the distribution of the placebos. It's outside of the placebos, but the probability that this would be in the placebo distribution is 1 out of 39, which is just so like, in any distribution, one of them is going to have that. One in any distribution, there will always be some extreme value, right? And then you interpret the p-value to say, the chance that that is from the placebo distribution is, never going to be 0, which again gets back to that claim that, we try to put together. That's how this exact p-value is interpreted. But it would be the conclusion for the state. You're right. I mean, the odds that state number 2 came from the placebo distribution is 2 out of 39. I'm seeing you type German, so I'm just kind of waiting. While you're typing, I'm going to show us where we're going. Let me put this over here. Well, what you're usually, I mean, you're looking for an extreme value. Ideally, it would, that's Fisher's kind of threshold to be, in that 0.05 range. That requires at least 20 units. I want to say that in the Spanish example with the Basque Country, I believe that it's 16 kingdoms. So I don't think it's possible to get under 0.05 in that case. So I remember hearing Abity say, in the case where you have a small number of units, then you're really looking more for extreme values. I think too, honestly, some of it is the evidence is in the visual. But if we could kind of return to it, German, and like keep this conversation going. I want you to continue to think and get your response. I'd like to get your response to this replication, or it's not even a replication. It's just to get your response to this assignment. Okay. And because you're going to see some challenges actually with this test statistic here in just a moment. So let me, yeah. So let's here. So this is going to be the replication. It's not a replication because there actually is no paper associated with this. This was a project of mine that we did write a paper. Me and Sam Khaing did write a paper using it. And I, in the end, just, it never got published. And we just it got orphaned. And so then I thought, well, this is a perfect synth paper. So I'm going to tell you, we're going to replicate. No, we're going to do something. Okay. So, and you can find the assignment. Like if you wanted to work on this yourself later, you can find the assignment at Causal Inference 3 under labs, under Texas here. Yeah, this one. And this is going to be, yeah, here's kind of a description. Okay. All right. So, sorry. So, United States, those of you that do not live in the United States has a very high prison population, both in levels, 2.1 million people in prison, state, federal prison, county jails. It's about 750,000 in the county jails, about 1.25 million in state prisons, federal prisons. And you got another 4.75 million on parole. From the early 70s to the present, it quintupled. So this is like history of prison. I only have state and federal prison. I got this from Bruce Western's book. And you can see here, state and federal prison, which is at least in the present, that's the one that's 1.25 million, jails 750. Anytime we add the jail in, it goes up. But it essentially hovered around 100 per 100,000. There doesn't appear to have been much pressure to grow the prison population. The prison population grows, for a couple of reasons. Crime grows, population growth, but this is per 100,000. So this is adjusting for population. But it kind of was settled into a bit of an equilibrium. And, when it's in an equilibrium like this, you don't need to build new prisons. You can use the same infrastructure for long stretches of time. Starting here in 1970, 1975, state and federal prisons grew. It's going to be mainly state prisons because they're the bulk of the prison population. So, you can't really pin it on one thing. But what appears to happen, and this is what Derek Neal and his co-author have written about in the Journal of Law and Economics, is that American states, state legislators, and voters began to increase the penalties, longer sentences on crime across the board. It's oftentimes it's blamed on the war on drugs, but if it's anything, it's like a war on crime, okay, of which drug possession and drug trafficking was one, but it's across the board. All right. Now, you cannot increase prison sentences, longer sentences. You cannot increase sentences and not have a larger stock of people in the prisons. So like the flow goes up. Well, this would predate Reagan. This would be in the 70s. But again, it's not really driven by federal policy. It's broadly state policy. And so you see here, the flow, if the flow of people into prison grows, if the flow of people into prison, but my point is that it's being driven by state policy, not federal policy. But putting that aside, the state level, if you have an increase in the flow of people going into prisons, then the stock has to grow if the sentence is getting longer. It just has to get bigger. And around here, something happens. It's not even very big. Look how it eventually gets up to 500 per 100,000. And if you include jails, it gets up to about 600. So here in 1980, it goes from, it's not the highest it had ever been. It had once during, I guess that's like a Great Recession era. But like around here in 1980, that's what it is nationally. So prisons have always been at capacity. That's the first thing. They've always been at capacity for a long time. So growth imprisonment, if you had growing imprisonment, it would typically bite on state corrections who really don't have capacity. And it's expensive to build prisons. So the way that people manage the flows, the way these Department of Criminal Justice will manage the flows is they build new prisons. That would be like a permanent increase in the prison population. But, that would be like, this is way over the population growth, okay? So you build new prisons, and you have to build a lot of them. You can overcrowd them you can let people out. And Texas, where I live, they chose to overcrowd. And there was a class action lawsuit in 1980. David Ruiz, he was an inmate who had taught himself the law, and he filed a class action lawsuit for human rights violations against the state of Texas, and filed it against or Texas Department of Corrections, and filed it against Estelle, who was the warden, which I think is just how you did it. It was against the whole Department of Corrections, and they lost, which was a surprise from everything I've read. There's a really good book called Texas Tough, tells the full history of the Texas prison system. And it was a lengthy period of appeals, but finally the appeals ran out. And when the appeals ran out, they started paroling. They could no longer overcrowd. They could not build new prisons. I mean, they could have, but the legislators wouldn't do it. So TDC only had one option, that was to parole. So this is about when they lost the appeals. Anytime, so we've got here this rising prison population. Okay, we've got that, and that's because it's rising. But as long as you're letting out people at the same rate, then the stock of people doesn't change. But if you're letting out people, if you're bringing in more people than you're letting out, then the prison population grows. So they sort of like, it's never exactly equal. So what they end up doing is they're paroling a lot to make room for people coming in. So they're just intensively paroling. I've never seen anybody try to study this part of the experiment. Okay, but right here, look, it gets pretty big. This means that, you know, when there's a gap, there's a big increase in the prison population. I don't know why it falls. This part of the history, I don't fully understand, but it falls fast. The exits are falling faster than the increases in, and so it's got this bigger gap. Or rather, at any given point, sorry, you've got more people coming in than you have exiting, okay? Which means that the total prison population is growing. Paroles are falling, though. And anytime the paroles are there, they make up the difference. But then something happens. 1991 to 1995, there's a governor. It's our last Democratic governor. It's our last female governor. She was the governor before George W. Bush. She's kind of like a famous cowgirl. You can Google her. I mean, she's just sort of like a very, you know, I don't know if she was beloved, but she could work with Republicans because of her personality. She managed to get a lot of prisons built. And I work with the TDCJ, the Department of Criminal Justice, to evaluate programs. And I've walked 6 times the prisons that were built. There are these huge prisons. They're called the 2200s, and they hold 2,200 people. And the number of prisons grew to 100 prisons across the state. I don't remember exactly what it was, but it was a lot. And the prison capacity grew 55,000 beds, for lack of a better word, in 1992 to 130,000 in 1995. All right. So they built new prisons. People always ask, was it private prisons? It was both. And it doesn't appear to be like, I couldn't find any pattern. So it's like what the prisons were like when David Ruiz filed his lawsuit. They were antebellum. They were basically antebellum prisons from the Civil War. Even now, not all of the prisons have air conditioning. I walked one prison that did not have air conditioning. What they have instead is these massive swamp fans. You could barely hear each other. There's like in every room, they're huge. So it wasn't really hot, but it definitely was not cold. And it was kind of this, it felt a little muggier. Well, back then I don't think they had that at all. So these were very different experiences, and they were overcrowded. There's a little bit of some activity by a guy named Governor Clement, but he doesn't get nearly as much built as Ann Richards. So Ann Richards gets, 13 built, 12 or 8, 9, 25, a bunch. This right here is the level, and this is like the percent change. So you can see there's a little bit of prison activity, but the overall capacity was kind of small. So it's like 40,000, 40,000, 40,000. You know, they're under supervision, so they're not building. This guy, Governor Clement, does build some. You can see it right here. Okay, there is some building of prisons, but the overall capacity should be like 1990 here. It's a little bit. The overall capacity is going up, but not a lot. So like right there, it's about 55,000. Then she begins to build like crazy. 33%, that's over here. 33% increase that year in prison capacity. 35% over the previous year. Prison capacity back to 33% over the previous year. So it's just huge growth. Actually starts growing at an increasing rate briefly, then kind of settles to around 130,000 by 2000 at 160. And I believe now it floats between 110, 130. And so here's just a plot. This isn't synthetic control. Here's just a plot. So you see it actually, Texas stayed pretty flat under that supervision while everybody else is growing. Briefly, Texas is below average, very briefly, right at average, but a little bit below average. Starts to catch up a little bit. Then there is some activity, but here's where the prison construction really starts. And then it flies up. And it goes up to 800 per 100,000 prisoners. And by like 1999, 400. So it's twice the number of the average state. Okay. So we're going to make this picture. All right. So we're going to make this picture together. We're going to start it off in Stata, and then I'll show you doing it in R too. Okay. And there is ways to do this very quickly in Stata, much better, but I like to do it the long way when I teach it because, first of all, it took me forever, and I am proud of myself, but also, pedagogically, I think it'll help you try to understand all this, like, test statistics stuff. So here's step one. Copy Texas. Go down here to your desktop or something. Copy it. You'll see why. All right. So move it out of there and let's go to open. We're going to go into the do subdirectory. There's also an R. We're going to go into the do subdirectory. We're going to open Texas Cent. Texas Cent. We got to change line 9. Let's go over here to File. Okay. Go down to Change Working Directory. And then you need to find where that is. Mine's going to go right there. So we're going to change the working directory wherever it is on your machine. Okay, that's the first thing. So I want you to do that. Again, you can ask the AI companion what I just said, but again, one more time. File, change working directory, click wherever you put it, do, okay? Choose it, copy and paste it, change line 9, right? All right, that's what you want to do. Now, the reason we're going to do that is we're going to be using this ... stuff. So just for the sake of making sure it's clear. So let's see, date modified. See, we're in here. There. All right. So we are in here and our data is in here. So we're going to use this ... command. I bet all of you know what I'm doing, and I don't even have to be teaching this stuff. But we're going to use this dot dot. So if you're in here, you go dot dot data. It basically goes dot dot, leaves the folder. Now it's like in this right here, slash data. Okay, it's like goes like this. Dot dot, you're up here. Slash data goes in here, grabs Texas. Okay, that's the first thing I need you to do. Second thing is, need you to install both of those. Oops. Just do it once, asterisk it out, so you don't have to do it again. All right. Now, at this point, what you need for this to work is you need a data subdirectory. You have to have a synth subdirectory. The way that I've made my code, you have to do it this way. You have to have a figures subdirectory. You have to have an inference subdirectory, and that's it. That's it. But what we're going to end up doing, you do have to have those. Otherwise, you're going to get an error, right? Okay, so let's load in our data. I don't have a great description of everything, but I'll walk you through what's in this data. So for those that aren't from the United States, state FIP is referring to a number that is given by the census to, it's called a FIPS code, and it marks a particular state with a number. So you can type in state FIP. Texas is 48. California is number 6. I believe that one is Illinois, but this is going to be our treatment state. Okay. What is some more stuff? Year. Race. What is that? I don't remember. So race is, don't remember what race is referring to. So black male prison is what that's going to be our outcome variable, black male prison. You also have white male prison, black male population, white male population, right? So we just said this. Not all balanced. Not all balanced. So if you ever play around with this yourself, there's some missing, there's 14 missing values on the white variable. You're gonna have to find them, and you're gonna have to recreate a balance panel because the data, XT set, the data has to be balanced. Okay, so it's gonna be state FIP. Our data runs 85 to 2000, and it's gonna be strongly balanced, right? We got year, right? I don't remember what that is. This is a crack index, crack cocaine index that Steve Levitt, Paul Heaton, Roland Fryer, and Kevin Murphy created using principal components analysis. Alcohol consumption, it won't run. Synthetic control won't run. At least this command won't. At least this command. The data package must be balanced. I'll show you in a minute, Wing Ching. You'll see it won't run. Alcohol. This is alcohol consumption per capita. This is average family income. Unemployment rate at the state level. This is all at the state level. State crack cocaine, state alcohol consumption per capita, state average income, state unemployment rate, state percent of the people that live under the poverty line, state percent of the population that is African American, state percent of the state population that is age 15 to 19, state level AIDS mortality per capita. Then I got, whereas state FIP is a number, state is a name. So like, for instance, tab state, if state FIP equal 48. So it gives me the name Texas. Okay. If I say tab state, if state equal Texas, it's going to give me a 48. Okay. So tab state FIP gives me numbers. Tab state gives me the names of states. And then the rest of, and then the rest of this right here is what I used to make this graph. I used it to make this graph. Probation, capacity rated. Actually, I used it to make that graph too, because this has got paroles. So that's the, or probation, capacity rated, operational design. So a lot of it's in here. I mean, I should probably clean it up, but I just haven't done that. And then I have African American imprisonment rate, white male prisoner rate, all at the state level. So remember, this is state level, state year, strongly balanced. It's just that WPM rate, it's not that it's imbalanced, it's that I've got missing values for those years. So it's like count if WMP rate equal, count if WMP rate equal period. I got 14 missing. Tab year if rate equal period. Looks like it's 85, 95, 90. All right. Tab state if W rate equal period. Yeah. So I don't know what's going on. So I don't analyze it. You'd probably, if you wanted to do this, you're gonna have to deal with that. You're gonna have to make it balanced, impute those, something. You're gonna have to make a decision and just be really clear about it. All right. So this is the syntax for the original Stata package in the original synthetic control Stata package. You call synth, outcome, and then this. You list your variables. So watch what I'm going to do. Notice how with cigarette sales per capita, I listed the year. I do that a lot here. Black male prisoner. So I'm looking at black male prisoners, not black male prisoner rate. Don't get too caught up in like, why'd you do that, Scott? And it's like, well, there's some lessons I want to show you by doing it this way. Okay. Black male prisoner. I pick the year. The way you pick that year is with the parentheses. So I'm using the pre-treatment characteristic of black male prisoners in 1990 in Texas. So it's be like, some BMP prison if state fib equal 48 and year equal 1990. 22,000. So that's my number. Okay. If I went like this, the rest of the country on average 6422. So Texas in 1990 has 22,000 prisoners. The average state number is 64, but it gets as big as 32,000. Okay, it's got a big standard deviation. Okay, so I put in 1, 2, 3, 4 pre-treatment characteristics leading up to the year of treatment, pretty much. I go 92, 91, 90, 88. Now you can always, this is all getting into the questions we were asking before, which is, why are you picking this stuff, Scott? And you're like, exactly. How am I picking these? That's, this is for purely pedagogical purposes, right? But you can kind of see, we can play around with it, all right? But that's my point is that this is all endogenous, just like that's endogenous. Endogenous meaning the researcher chose those. They're not popping out of any kind of model. All right. Your goal here is really to fit the line. That's what your goal is trying to do. You're trying to create a picture that looks that good. Okay. But it opens it up to tons of p hacking or cherry picking. So I got all these in here. All right. I'll list them all. If I put a number, that means that's that year's pre-treatment characteristic. If I don't put a number, like income, then it's the pre-treatment for Texas for the entire pre-treatment period. On average, people were the average income in Texas was $16,108. You could list it. and that column right there on average is equal to 16,000. Okay. Comma, and now like you just have to give it a lot of syntax. Say treatment unit 48. And that 48 is coming from the fact that I did this. I told Stata that my time variable was year. And I told Stata that my panel variable was state FIP. So it knows that the panel unit is state FIP. And I've said state 48. State FIP 48 is the treated unit. Treatment period, 1993. Unit names, state. Now remember, that's the number, and that's the word. And the reason we do that is because we're going to actually like make little words here. Okay. Unit names. MSE period, what is that referring to? Let me just real quick get back to where I was. Estimating the V matrix, minimizing the mean square prediction error for the pre-treatment period, choosing V that minimizes the mean square prediction error. That's what I'm doing right here. I'm saying minimize the mean square prediction error for those years. And then show me all the data. So I could actually not show all the data, and I could just do this. And not peek at the results. And that would just be that would be like, just showing that. Okay. But I'm going to not do that. Do the whole thing. Last thing, what it's going to do is it's going to store a data set called synth BMP rate, and it's storing it here. Where is it storing it? In data here. Synth BMP rate. So let's find it. Today at 142. So it made that one. Let's look at that one. Actually, let's not look at it yet. So then it says replace it. It says fig, semicolon, and then look, we're going to get our V matrix. Okay, we're going to get our V matrix. So let's look at this. All right, now every point here is referring to actual realized outcomes, and this is referring to imputed counterfactuals. Synthetic Texas is a estimated counterfactual. It's no different than any other causal method. Okay, every causal method is doing this kind of thing. It's just some of them are doing it more obviously than others. All right, so let's look carefully. When would I not? I don't know. Do you remember what they say? Did they just leave it as the identity matrix? Treat all the covariates the same? That could have been an updated in the JASA. Yeah, shows up in the code. The JASA has a lot more details. A lot more details. So, this idea of which of the covariates are you going to treat differently? I mean, I'm not sure, what kind of modifications they began to do, but some of the stuff in the 2010 JASA is not in the 2003 AER, but that data can be estimated with the 2010 code. And it, you know, it was always there. So it was always doing the same distance minimization. So I probably had to guess, Caesar, it's using like, you know, the V matrix just has to be K by K positive semi-definite. Yeah, has to be symmetric and positive semi-definite. So I suspect it's just a diagonal of ones. That's probably what they did. Treat all the covariates the same. Because I bet. I can't really imagine wanting to do that because if you did that, you're kind of guaranteeing if you do that, you're guaranteeing that it won't have the minimum, you won't be minimizing the prediction error, which means that some of this that you're going to get in the post-treatment period could just be coming from the prediction error and you're trying to get rid of it. That's my hunch, but I'm not sure. I've never seen anybody do it. All right, let's look at this. First of all, root mean square prediction error pre-treatment. Oops. Root mean square prediction error pre-treatment. What is this? Here we go. The average discrepancy of each of these numbers vertically squared, summed average square root. Okay. So you take all of these, square them, sum them, take the average, take the square root. It's equal to 1,295, which means what? Our fit is off on average by 1,295 African-American men. Okay. That's how much we are off. All right. So keep that in mind. Here is our table of unit weights, the W's. Okay. Most of this dashed line is California. 41% of it is California. 11% is Florida. 36% is Illinois. 12% is Louisiana. These are fairly large incarcerating states. So it sort of makes sense that those would be like Texas. The rest are getting dropped. Not dropped. The rest of them are getting a weight of 0. Probably Stata was, or probably, you know, they were wanting to get negative weights, but it won't let them. So it won't, they get pushed at the corner. And since the weights have to sum to 1, everything else is getting compressed on here, getting reallocated to these. Okay. Here is this table minus this part, real versus synthetic, treated versus synthetic of my 13 pre-treatment characteristics. This right here is the small, that these numbers, the weights that produced that column. If I even tweaked the weights a little bit, yeah, it is very common. It is very common for many units to get 0. It's this sparsity is pretty much is one of the most, yeah, it's like a characteristic of synthetic control. If I was to take these weights right here and I was to change this to 0.121 and make that one, you know, 0.362, okay? Or whatever to make it balance out. The average discrepancy would go up. Yeah, in effect, it is. Exactly. I mean, technically, it's like, yeah, it's all of these times Y or times X, but exactly, they're all canceling out. So it's just a weighted average of 4 states. And they look like Texas. They're not perfect on the covariates, but they are very close. This is as small as it can be. Cannot get any closer. It is possible that you could get one of them closer, but if you tweak the weight, the overall average matching discrepancy, remember the sum, okay, it's actually this. We change that weight at all, we get a sum. We will necessarily go in a suboptimal direction, okay? Okay, and here's our V matrix. What's getting the most important in trying to minimize mean squared error? Okay. 0.042, this is African American imprisonment in 1990. 0.04, 1992, 0.14, 91, 0.05, 88, 0.04. Okay. Now these are interesting, and I'm not going to try to give you what I believe is it, but alcohol consumption per capita is absolutely irrelevant. It's absolutely irrelevant. AIDS mortality is not irrelevant. It's 1.5, 1.6. There's there's a very high AIDS mortality rate during this time, but income, unemployment, and poverty are irrelevant. They are not important. So in that summing of total matching discrepancies, these are really just getting assigned to zero. They're getting assigned to zero. So when it's doing down here and it's like going through all 13 of them, 4 of them have a zero. They're just getting ignored. The ones that are really driving it are right here. What percent of the state is African American? 1990, 91, 92. Now, the reason why this is relevant is because our outcome is black male prisoners, not black male prisoner rate. If I had done BMP rate, assuming it actually runs, well, they're still pretty big. Oh, but now the outcomes don't even really do anything. Do we get different states? Arkansas, District of Columbia, Illinois, Indiana, California's not even contributing now. Montana, New York, yeah, it's a bunch of them. And if we look at the root mean square prediction error, you can't really compare them because one was in levels and one was in rates. But that does look good. That does look good, but we're not going to do that. We're going to do black male prisoner. Okay. Now what I'm going to do is I'm going to load up the reason is the reason, Winching, is that my model used rates in the actual estimation. And, so it's a different model. And they're very, very different. Lots of states might have similar African-American rates, but levels not at all. Because in the United States, African-Americans live predominantly, in the South, parts of the West, New York, California. They're not randomly distributed across the United States. They've like sorted into particular states. So, if you adjust for the population, you might have comparable imprisonment rates. But if you just look at the levels, African Americans are really only going to be in areas where there are African Americans, which is why these variables are driving so much. But yes, the control group is only those states that have positive weights. Yeah. All right, so we ran this. Let's pull this up. All right, so column 1 and 2 contains our weights, and columns 3, 4, 5 contain these numbers here are these numbers. So like time is that one. Y treated is referring to the black line. So you can see like 1985, it's like 15,000. The dashed line is this one. It's below it, 13,000. Okay, you can kind of check, so the black line here jumps above the dash line. In 1993 is it's going to jump here. Boom, 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 boom. So we're going to use this. We're going to use this right now for generating our event study. Okay. All right, so there's our event study. Pretty similar. Gap in per capita cigarette sales, gap in black male prisoner prediction error. You can call it whatever. And you can sort what you're looking for is something that's close to zero pre-treatment. Just like in a diff and diff event study. And then this is the post-treatment out of sample prediction. And every one of the lines, every one of the points post vertical line is interpreted as an ATT. So like right here by 95, there are 25,000 additional black men, 25,000 additional black men in prison than would have been in prison had they not built the prisons, right? And then it just levels, stays there. 25,000 every year. There are 25,000 additional black men. So if we go back up here, so it's 95, 55,602 minus 303.99, 25,203, 25,000. That's about what that is right there. Okay. All right. So next step, inference. To assess the significance, we calculate exact p-values under Fisher-Sharp null using a test statistic. Fisher-Sharp null always requires a test statistic that is based on outcome and treatment. So we could do it two different ways. We could use as our test statistic, we could use this, the size of the output gap. Like we could, because Fisher-Sharp null does not tell you what your test statistic needs to be. It just needs to be something based on the treatment and the outcome. Using a treatment effect is usually what it does. So we could do this, but we want to, what we're going to do is we're going to scale it by the pre-treatment value. So hold on one second. Eduardo says, what's the name of the states mean in this table? Here? Right here? Is that what you mean, Eduardo? Or what line are you thinking of? This part? Numbers of the graph. Oh, here. California 408. Okay. California 408. Column 1 and 2 is the vector of weights. Columns 3 to 5 is creating the synthetic control. Basically, the way they wrote it was they just kind of put the two pieces of information that they think that you're going to probably want to keep. they put them in the same data set. So column 1 and 2 is just your collection of weights, and then column 3 through 5 is what we're going to use to generate our placebos. Right, while this is running in the back, I am going to do this. So look, watch what's going on. Watch these numbers. See this? They're changing. See that? See how they're changing? Why are they changing? All right. So remember, under this exact p-value method, you iteratively apply the synthetic method to each country state in the donor pool and obtain a distribution of placebo effects. So this is what it's doing. It's cycling through all the states, including Texas right here. Every time it's doing a placebo, it puts Texas back in. Because under the null, Texas has no effect. It runs the exact same model, comma, except for right there. It's the one thing that's different. It had said 48. Now it's going to go through the fake states, or the real states, but there's no treatment in those states. Okay? All right, we'll look at this in a second. So everything else is the same. Okay? Then what it's going to do is it's going to generate the picture. It's going to generate the picture, and it's going to save it here. It's going to save it here in under cent gap BMP rate. And what that is right here. It's saved. So like this right here is Texas. This right here is California. Okay, all it did was it ran through every single state, opened it up, renamed it, dropped it if it was a year, renamed time as year, renamed this as treat, name of the number, this synthetic, they named it counterfact, or I did. Then it calculates what I call the gap, which would just be an individual treatment effect, which is basically just California minus synthetic California. Saved it. Okay, does that year by year. Because what that's going to do is I'm going to get a gap per year. What am I going to use a gap per year for? These are the gaps right here. These are the gaps per year. You can see it better right here. This is the smoking gap. So when I did this right here, when I created that by year and then saved it, I have right now all of these little squiggly lines. They're just in their own separate data set. They're all right here. They're in their own separate data set. Now I'm going to merge it. I merge it. Now it's all inside placebo BMP rate, which is right there. That's why it's a little bigger, because it's all these things. Then what I've got to do is I've got to calculate the, here, get this ratio of the post to the pre-treatment root mean squared prediction error. How am I going to do it? Well, I did it over here. I need to kind of make this look a little prettier, but I wonder if I could do that. I need to make it, it's doing something, it's doing something in here, whatever. So I've got some kind of thing set up to do this, but, oh, I bet it's when I exported it here. Yeah, there's a way to get these off. Anyway, so, all right. And this gets back, I believe, Eduardo, this was your point, or Caesar's, no, German. I think this was German's point. I want to show you something. So what I did was I calculated the root mean squared prediction error twice. Calculate the root mean squared prediction error here. Okay. Calculate the root mean squared prediction error here. So here's how you do it. Here's how I did it. Open up each of those placebo states. Calculate the squaring. This times itself. So if it's negative, it gets turned into a positive. Then take the average of the post mean. So it's going to take the average of this, which is to say sum it, divide by the number of years. Do it for the pre over here. Then take the root mean squared prediction error for this one and this one, but it's going to do it like right there, and then it's going to do it right there. So it does it, you know, right there, right there. Oh no, yeah, it does it for the whole thing, and then it takes the ratio of this one over that one. Ratio there. And then I keep the root mean square post and pre, and then I keep it in this matrix. MK mat was what we installed. No, mat2txt was here. No, there it was. There. All right, so we got all that stuff stored. All right. Then yeah, this is this SCO. Okay. Yeah, I don't need that. So then you've got to put it all in here. We save it. You know, there's got to be an easier way to do all this. But anyway, in sheet it done it. All right. So let's look at this. What's in this information? So all of this information is coming from me calculating root mean square prediction error ratio for all the placebos and Texas. And look, Texas is number 2. Texas has the second largest ratio of the root mean square prediction error in the post to the pre. Okay, it's got the second largest. Who has the largest? Illinois has the largest. Okay, now you can see why this is the case. Look, 23569.021 divided by 1296. $18.18. Okay, so that number right there, the root mean square prediction error in the post-treatment period, which is basically the average treatment effect, okay, because it's basically the average of that, which is a rough approximation to the average treatment effect, it's 18 times larger than the baseline. All right. This is Illinois. Illinois' treatment effect is only 6,500, but that's 19 times larger. And the reason why this is like, you know, happening is the fit is so good pre-treatment that even a smaller post-treatment test statistic can cause the ratio to grow. I don't know if this, like, I don't know if the name, I mean, I've heard people say, it's not powered right or whatever, but like this is possible with this. But I started digging into this a little bit, and I wanted to, before I show it to you, that's how the p-value was literally calculated. I sorted it in order of the ratio. So if you look, I sort by ratio. I then generate a rank. Then I generate a p-value, which is the rank over 46. And the probability that this would be generated by chance is 0.043. But the probability that Illinois would be generated by chance is a 0.02. So I kind of want to look at this a little bit more. What the heck's going on with Louisiana? But before I do that, I got to make this crazy spaghetti plot right here. Because if you remember, I stored everything here. I merged everything together. All of these individual gaps, these little event studies are there. So I'm going to do it here. All the placebos in the same picture. All right. So like these states right here are outliers. Even a set of weights that minimize that distance function, okay, minimize the sum of those squared matching discrepancies, you still end up with these states that have extremely high incarceration rates such that no one can come close, right? So like, which states are those? 11, 28, 32, 33. Let's see. Okay. Tab state if state FIP equal 11. DC, the Washington, DC has just an astronomical crime problems and prison problems. So tab state if state FIP equal 28. Mississippi, that's where I'm from. State FIP equal, Mississippi has a very large African-American population. That could be a part of it. 32, Nevada. Now that is strange. Don't know what that's about. Tab state if state FIP equal 33. New Hampshire. Don't know what that's. Oh, I know what it's about. I know exactly what it's about. It's these guys. It's the low ones. It's the low ones. You can have really high incarceration such that nobody's close, and you can have really small ones such that nobody's close. Yeah, exactly. So then we'll see what this last guy is. Tab state if state FIP equal 41. Oregon. So probably like no African Americans live in Oregon. None of them live in New Hampshire. None of them live in Nevada. So I'm assuming probably it's some of these people, but these are probably Mississippi and DC. It's one ATT estimate. None of these should be, none of the placebos, none of these should be interpreted as ATTs. These are placebos because they did not build prisons in these states. These states did not build prisons. If they did build prisons, you have to drop them. I dropped 5 states. I dropped 5 states that actually did do some prison construction, so I dropped them. So none of this can be an ATT because there is no treatment. These are just the distribution of basically the out of sample prediction of a model like this that just has poor prediction. Okay. So I do that. Save it in figures. But what I'm going to do now is I'm going to drop those 5 states that are like these guys, definitely those 2, and I don't know who these other ones are, but what I did was I dropped anybody whose root mean square prediction error was 5 times more than Texas. And if we go back and we looked at those pre-treatment root mean square prediction error, okay, we sorted it by root mean square prediction error, sort root mean square prediction error pre G sort mean square prediction pre. All right, and I said what I did was I dropped anybody whose root mean square prediction error was 5 times bigger than Texas. Texas is where? It's like 1,200 and something. These. So I'm going to drop 6, 11, 28, and 36. Okay, I didn't do it right. So I should only be dropping. Oh, I did drop 6. I did drop 11. All right, so I am doing some of this right. I left that blank. 6, 11, 28. Dropped it. I don't know why I dropped 32. I shouldn't be dropping 32. Actually, I'm just going to drop anyone who's is larger. Let's just do it that way. 1, 2, 3, 4. So we'll just go 6, 11, 28, 36. 32, we'll put him back in. Okay, we'll just do it like that. All right, so we'll drop those, which is what Abity did here. See, so Abity starts going through the same kind of thing, shows everybody, starts to drop the outliers, get it closer to the ones that look just like it. Pre-treatment only, yes, Yinju. And, it's really purely for aesthetic. purposes. And I will say this, Yingju, that what they advised doing in this original paper, nobody really does. We used to do it in our paper, but ultimately it's a lot, it uses a lot of space. It uses a lot of space. I think it is helpful to kind of trim it a little bit for visual purposes, but you don't trim it for the calculation of the p-value. Okay. But let me show you one thing and I'm gonna let us take a break. That Illinois thing. That Illinois thing was weird, because I mean, Texas literally has look at the size of the treatment effects. This is the size of the treatment effects. This is the ATT. Illinois gets 6,500 more prisoners. Texas gets 23,000. Nothing else is in that level. Nothing else is even, there's one in the thousands, 3,000, but nothing's in the 23,000. So what the heck's going on? So then I went in here and I was like, all right, I got to just see this with my own eyes. Let me just look at both of these. All right, so you can see why Illinois is, quote, winning, because its fit is so good. Its fit is so good. So when you denominate it, you're almost dividing by a infinitesimally small number, right? And that's going to blow up the ratio, even though the treatment effect is much larger. So you got to have a good fit. You got to have a good fit even to kind of survive these weird events. But look more closely at this, okay? First of all, Illinois is finding a negative effect. We found a positive effect. Illinois found a negative effect. The root mean squared prediction error always turns into a positive number. If you go back here and you look at the root mean squared prediction error, it's always positive. Why? Because it squares each of the gaps. So even though this right here is negative, in the actual statistic that you're put out, it'll be positive. So I highly encourage you to really look at these and see what this is. So that's one thing. And the second thing is they are the mirror image of each other. When this one is going up, this one is going down. There's an inflection point right there. There's an inflection point right there. It hits a top on year 95. It hits a min at 95. It levels out. It levels out. I was like, something's fishy. So I went back up here and I was like, let me look at this again. Just at Illinois. I don't like using synth runner, to be honest, because I just think it's burying too much. And, I like all the control over it that I have, but a lot of people like synth runner and those standardized p-values. I just think, that's not in the original JASA. So I don't do it. I mean, I guess what they're doing for those standardized p-values is they're getting, p-values per year or something. But notice what's going on here. Yeah, I'll show you the process in R. So what we have right here is this is Illinois. This is Illinois. Look, it never changes. What changes is what? The placebo, the synthetic Illinois. That's the negative treatment effect. The negative treatment effect is coming from synthetic Illinois ships. Let's look at who synthetic Illinois is. Alabama, Florida, Ohio, Tennessee, and Texas. Texas got put in. Texas is part of the minimizing. So then I run it again without Texas. And it's not there. So where am I going with all this? You've got to be thoughtful about all this. You need to look closely at all this output and be really, really scrutinize it. I don't think you can do anything other than report that p-value. You could obviously drop Texas and then run it again or illustrate it or something like that. You could definitely do that. In fact, you can get the test statistic. You know, if you just simply use all the pre-treatment values, Illinois won't come in first. But point is that this particular approach to randomization inference is not necessarily like foolproof. And so later work has changed that inference. Let's look at it in R. There are several R packages that you can use. Let's look at the original. No, this is the newest. Kyle really likes this one. This is the SCPI command. Whoops, where'd y'all go? I haven't played around with this too much, but Kyle really likes this SCPI. SCPI Cataneo. So this comes from software by Mateus Cataneo, SCPI. He's written a little bit on synthetic controls. So I'll show you here. Oh, I'm sorry, I didn't see those chats. Sorry, Anna, I didn't see this. You could do RD, yeah, but you know, Anna, if you did RD, I don't think it's really probably advised to use RD with year. You know, you're really wanting fairly fine. I mean, if you used RD with year, your bandwidths are probably gonna be the whole sample. You know, you're gonna have like, you know, all of this probably in all of this, in which case it's just gonna be pre and post. But if you had, you know, daily data, monthly data. But you know, for this, the thing is, you know, you don't really see any effects for another couple of years, you know. So RD in time may miss some of these long run effects. And that's some of the challenges with RD in time, is that it's so, you know, so close in time. Okay, so we have here SCPI provides Python R stated implementations of estimation for it. You got Python implementation, R, and Stata. All right, so let's look at it. I have not run this. Here we go. You're not supposed to, Winchin. Everybody asks me that. You are not supposed to do that. Under the sharp null, there is no treatment effect. So you're supposed to be leaving California in there. You know? When Abity talks about these kinds of things, he gets real pragmatic. You know? I think what I would do is I would probably drop it. I just would be very clear about it in the paper. You know, I would say, look, we analyzed this. This Texas is driving the result of another state. Because why? Because the treatment effect is so massive in Texas that if it shows up as a control anywhere, it drives the synthetic. It is, yeah. Well, it's like they're all, isn't it wrong? Is it wrong? Is it wrong? Is it wrong? It's the out of sample prediction. It's the out of sample prediction using the best model on the pre-treatment. So is it wrong? It's definitely not able to predict what was happening because there's a treated unit in its control group. But I think like unless I'm wrong, and if you guys want to correct me, I mean, my understanding is that you do not drop the treated unit when you're doing randomization inference. But it does seem kind of weird that you wouldn't a little bit to me, because if the treatment effect is gigantic, it seems like it would start to do weird things in the distribution of the placebo distribution. But I'm not positive that that's what is recommended. If we want to do some homework, I mean, I can look and see, but as I understand it, that's not right. But I could be wrong. Well, it does for some. It does, Winston, for some. I think what I would say is different from that. I would say that, the distribution of the placebos, okay, the distribution of the placebo says what? It says here is a weighted average of every other state. That if we were to scrutinize it, how well did it look pre-treatment? How well did it look pre-treatment? Some of them don't look well pre-treatment, and post-treatment they don't look well either. But I think what we end up saying is that, this model that was chosen, like, let's just pick this model. Hey, Simba, this model right here. Well, that model may not be a very good model for every state. Okay? May not be a very good model for every state. Trying to model African American imprisonment in South Dakota using the model I gave it might not be able to reproduce the time path of Black male imprisonment in South Dakota very well. So what this is kind of doing, this is basically saying, here's this model. This is what this model's out of sample prediction looks like, right? Sometimes it's really bad. Sometimes it's perfect. But this is the distribution of that like post-treatment prediction when there is no treatment. That's all it says. Okay. Does that make sense, Winchin? I don't know if I feel like that may not, I get the sense it's not very satisfying of an answer. Okay. All right. So we're going to create a treatment variable here. All right. We're going to do synthetic control off of ABITY. Uses aug-synth, augmented synthetic control, which is what we're going to use next. But under prog-func, we're going to say none. All right. We're going to say none. We're going to run it. It's running it. All right. So it ran it. It just gets so weird when it does it, but we're going to plot it with the jackknife. I'm not crazy about this at all. I plot it with the jackknife. The jackknife, there's a method of a jackknife that'll actually give you confidence intervals that is not there in the original 2010. Okay. It's not there in the original 2010. Then I can make the spaghetti plot. There we go. So, Eduardo, it's through line 77. It's through line 77. Same picture though. Now, I will say that you will find different answers, unfortunately, if you do synthetic control with R versus Stata. Now, I don't know that about the SCPI, but I know that for the original synthetic control, it's right here. synth.r. The original synthetic control, synth.r, just doesn't work well. It's just like it will take forever to run. but this is the one that was originally made. So here it is, creates that. Now it's making the placebos. All right, so it made the plots. Let's see. Here it is. It makes this. Okay. Then makes the event study. Does not put the dash there, but the original command is use the data. You say the predictors. If you're gonna just put the predictors in and use the averages, you just list them, poverty income. The original synth package in R gives you just as much flexibility as mine did by putting in lots of different things. So you put in here predictors, poverty income, and then you say, you know, what you want, the average. Time predictors prior, this is going to be what you're going to search over. Then you do these things called special predictors. What's that? Special predictors are anything that has the years after them. So I say, all right, black male prison, alcohol, AIDS, black, percent 15, 19, and I list them out. Dependent variable, black male prison, state FIP, state, year, say my treatment identifier. I list my controls, my optimization here. This is I believe this is the minimizing of the mean squared error. And then I plot the data. Spits it out in the synth out. Plots it. Path plot, that's this one. No. Path plot, that's this one. If you have more than one outcome variable, you're gonna have to run it. You're gonna have to run it more than once, and it's gonna be a different model. It's gonna be a different model. You know, I mean, you're not gonna end up with the same states. People get really hung up on that. There's no reason why the states should be the same. I mean, just because a weighted average of states gives you employment in one state doesn't mean that it would give you I don't know, STD rates. Why would they be the same? Because it's purely mechanical. It's purely mechanical. You're just trying to minimize the sum of the squared matching discrepancies. There's no, they don't have like an agreement with each other that like if it's minimum on one, it'll be minimum on another. But see how long this has taken? The placebos, it takes forever on this. So it's got this gaps plot. There's the gaps plot here. To do these placebos. Let's go back to this one over here. But basically, this one will go fast, but let me show you something. Notice I have no covariates. I have no covariates listed. This augmented synthetic control command uses for covariates all the pre-treatment lags. And it doesn't give you any options. So if you're wanting to like be selective, you have to like use something like this one, which takes, a year to run. Special predictors are going to be these ones with specific years. Best I can tell. These are just going to be the averages. Still not done. Let's take a 15-minute break and maybe it'll be done. Let's take a 15-minute break. We're 30 minutes, 5 minutes over the break. So we'll come right back. 15 minutes, that's 10, 45, 50, 49. We'll come back at 49 minutes on the hour. All right, see you in a second. See you for a second. We've been this pretty exhaustive. I hope that's okay to go this deep on coding. And we're now gonna just real quick show you how here it finally finished. Okay, it finally finished. And then I plotted it, plot the placebos here. Okay, so there they are. And then if I want to plot the histogram, there's Texas, there's Illinois. I believe that's Illinois. So probably dig into here and find some more stuff. Because it's inside plot, it's inside placebos. It's probably in here. So I could probably play around with this and find a little bit more, but so but that, Eduardo, that is another package. It is. Well, excluding, what do you mean? Excluding the lagged outcomes, but then putting in an outcome? I don't understand. What's the difference? Here, let me put this so everybody can see the comments. Uh, let's look at this next one. This next thing that we're going to do is going to address this. Okay. So what we're about to do next is getting into what's called the cherry picking. All right. So this is a paper that we wrote with John Colley, Julia Edelbuttel, Matt Eisenberg, and Alan Matthews. And it's about how this one scandal where the spokesperson for the Subway franchise was arrested for child pornography and sex with a minor. Happened in 2015. This guy, Jared Fogle, for those that don't remember, I think he was the pitch man for Subway for a long, long time. He had been very overweight, lost the weight, became very thin. He lost the weight just eating Subways. And synthetic control is more appropriate. Well, that's a complicated question. Synthetic control does not use a parallel trends assumption. We actually haven't really dug into what exactly is the assumption that drives synthetic control. Callaway-Santana, the robust difference in differences estimator, is to be used when you can satisfy conditional parallel trends or parallel trends, right? That's the core. Synthetic control does not use a parallel trend, all right? So we really don't know yet what exactly is under the hood, all right? Secondly, Callaway-Santana can handle multiple treatment groups. Right now, we're looking at the single treated unit, but we're going to later tomorrow get into these situations where there are models that will be similar to Callaway-Santana applications, but the underlying assumptions will be a little bit different. So I would say that right now, synthetic control is being used to study an individually treated unit. And as it has expanded, it has been expanded to accommodate other situations, including multiple treated units, multiple time periods, and it never uses a parallel trend assumption, but it uses something else. So I would, that's not the best answer because some of this stuff is coming, but that's how I would just say, Wenchen, is everything we know right now is that the original Avity is for the single treated unit. Okay. So this is a Subway. When he was arrested, you can see here the number of TV stories that came out about Jared Fogle shot up when he was arrested. Google Trends literally went as high as it can go. And so here's our estimate using data on households purchasing food. So we knew where these households were purchasing food, and we wanted to know, well, what is the effect of this event on people going to Subway, right? So as our baseline model is this, Subway is the circle, and synthetic subway is the diamond, and here's the treatment, and these are the waves. Waves are not years, but these are the waves, and there's no effect. No, there is no effect that we can find of learning that the pitch man, of them firing the pitch man under these circumstances. So then what we did, we sort of changed the y-axis to make it a little bit, because here it was going from 0 to 0.3. Here we're going to go from 0.2 to 0.3 just to center it. Some of these decisions you make are aesthetic, okay, just to kind of, because there's so much white space here, it's compressing variation. Here we sort of get rid of some of that white space a little bit and allow it, but we still don't see anything. Here we have our estimate. That's McDonald's. Remember, to minimize, this is our placebos. Nothing happened to McDonald's. So we're going to drop McDonald's. All right. And here's our treatment effect. All right. It's not a great fit pre-treatment. And we can't really find, there is this like, decline there. It's 4 to 5 waves later. All right. So Abity recommends a nested minimization problem using the pre-intervention data. This came up earlier, so this is anticipating it, but he really doesn't give any guidance. He says he recommends a really just an algorithmic minimization. That's it. But he does not provide any guidance over the selection of the model, right? Like, and that's when a lot of our questions, like Caesar asking, if I don't want to put in GDP in 1998, but I just want to put in GDP, the average of GDP, right? So this is the thing. There's almost like so much you could do. There's so much subjective, decision making because there had been no guidance. Because usually what people were doing, and I can speak for myself, that's what I was doing, was I was just trying to fit the model. I was just trying to get something that looked like this. That's what I was trying to do. I wanted something that looked good, pre-treatment fit. And there was a lot of data mining involved in that. And that's what was really felt awkward, was all this data mining. All of a sudden you sort of felt like you were back in the world of like picking your synthetic control. So Bruno Furman, Chris Pinto, and Vitor Postbaum. Furman and Pinto have done a lot of work on synthetic control. They were like early econometricians, young people that were working on this. And they just suggest a few specific specifications kind of addresses all these questions, okay? And they say report all of them. Report all of these specifications, do it with and without covariates. And here's sort of an example of the kinds of tables and graphical evidence that they suggest researchers do. These are 14 different specifications here of the p-values. Now, what's the A mean and what's the B? So let's go through the numbers. One is always report a model that used all pre-treatment outcome values. That seems to be the thing that is now highly sort of suggested. Secondly, put in the first 3/4 of the pre-treatment outcome values, the first half, odd numbers, even numbers, pre-treatment outcome mean, and 3 outcome values. Okay. Do it without covariates. And if you believe there are covariate values that you believe for your own theoretical reasons that you should be conditioning on, then do those too. But report all of them. Report the p-value. Then report a spaghetti plot. But this is not a spaghetti plot of the placebos. This is a spaghetti plot of all 14 models. Show all 14 models. Now you can still have a preferred estimate. There's nothing wrong with having a preferred estimate. But what they're saying is these particular specifications in the infinitely large sample can't be hacked. In the finite sample, they still can be. So report all of them. Okay, so that the reader can see that this really is robust. this is really a fairly robust result. So this is the robustness result for the synthetic control. Show the visualization. Once you have your preferred estimate, okay, then show the placebo on the preferred estimate. But what you would be wanting to do is take this one and do all 14 of those and then show a distribution of that. You could do that in Stata too. It's not going to be hard. We did it in Stata, but it'll require some actual coding. Okay, it'll require some actual coding. So this is what we did. We did all pre-treatment outcome values with and without, first 3/4, with and without, first half, with and without, odd, with and without, even without. Reported it. It never really mattered. It never really mattered. It's like, you know, we never really get convincing evidence that, you know, there was nothing that we could find that convinced us that we were able to say the Jared Fogle getting arrested was having much of an impact on people visiting the franchise. Okay. So to summarize, all right, so that is probably, in my opinion, to kind of get back to this, in my opinion, when you're thinking about, well, should I do this? Should I do that? I think what you should do is follow Furman, Pinto, and Postbaum and do all of those specifications. And of those, have a reason for your preferred one. But that's what I recommend that you do. Otherwise, it's just going to be, that's why they call their paper cherry picking synthetic control. You want to avoid that. You want to avoid that kind of cherry picking of your synthetic control, which is when, and the reason it's cherry picking is because you're just making all these choices that don't have a correct answer. You know, like when Caesar's asking, should I do this or that? The question is, well, what's the objective function? There's not really any clear answer to it. You know, either one of those will have a unique set of weights that minimizes the sum of the squared matching discrepancies. But, you know, early papers were just all over the place in terms of what practice people did. So that's what I would recommend. That's what I would recommend doing. So the method is very simple, right? Just kind of summarize, take a donor pool, find a combination of units, weight them non-negatively, minimize a distance function subject to two weight constraints for W star and V star. Question is, what is the bias? What is the bias of this method? And what can we do when we think the bias is severe? So now we're going to look at the bias in synthetic control. So usually it's motivated, and it doesn't have to always be motivated with the factor model, but Abity sort of says, well, assume there's a factor model that's driving the potential outcomes, right? And this is what he describes. It's something kind of like a two-way fixed effects. It's not exactly a two-way fixed effects. It's like you've got here, all right, you've got this time dimension. This could be like recessions or something, some annual shock, all right, some Z term, which is observable, but the Z's have coefficients that change over time. So you've got some kind of fixed characteristic that is having a differential impact by year, and then you've got some unobservable that's having a differential impact by year, and then you've got this error. All right, so this is called a factor model. And Abity says, well, assume that the factor model is what generates Y0. And the reason why he says Y0 is because we're missing Y0. We're missing Y0. All right. So Z is going to be the observed features. Z is going to be the observed features. So that'd be like the stuff like, you know, AIDS mortality per capita, whatever, all those things. U are unobserved. It's the factor loading exposure to the shocks. Lambda T is the set of factors. UI is the unobserved features. I think that's wrong. I think that's supposed to be theta T. unitized factor loading. That's supposed to be lambda t right there. So this is lambda t is what's the deal? So this is z observed feature. And this is the factor loading on z. It's a set of factors that are kind of time related. And then there's this U unobserved heterogeneity. And that right there, it should be lambda. I gotta go back over my notes here. But for example, lambda t is a shock to the returns to the technological ability. UI is the unobserved ability. So you can think of it as like there's something that happens that makes unobservability suddenly more impactful. So it's different than a panel. Usually in a panel model, there is no factor loading. It's just UI that doesn't change over time. And you can like first difference it out or something like that. Now we've got time varying heterogeneity. Okay. So suppose that we minimized the distance between treatment state and weighted average of the control states, right? And that would be when we apply those W's to the control states. Now let's say that we found that it equaled Texas. Let's say the weighted average of the control states equals Texas year to year. Now let's say that the weighted average of the observables equals Texas's observable in that year, and so on, right? Can only hold approximately in the sample, but if you're able to do that, you can establish a bound on the bias of the estimator. And here's the bound. So here's the bias right here, right? Y0 for 1 minus the weighted average. If the summation T0 to equal 1, here we go. Where is that? Lambda here. All right, so that says n equal 1. I think it's supposed to be n equal 1. If that right there is non-singular, then this whole thing, this right-hand side will be close to 0, okay? That will be close to 0 if the number of pre-intervention periods is large relative to the size of the transitory shocks. If it's large, then these will cancel out because they're just idiosyncratic noise. I think I had it right here. Unit level transitory shocks. So we need the number of time series to be large relative to the size of the transitory shock. So any kind of transitory shock that does happen has got to be like on average equal to 0 for both Texas and everybody else, so long as that's non-singular. So only units that are alike in observables and unobservables should produce, this is the logic of it, should produce similar trajectories of the outcome variable over long stretches of time. So Abity shows the bounds on the bias, and the bounds on those biases, on that bias, is based on, not surprisingly, how well you can fit the synthetic control to the treatment group over time. The bias bound is controlled by a ratio between the scale of the error term and the time length. So you need that time length to be long relative to the size of the error term, which is what I said right here. Okay. So your credibility of a synthetic control estimator, and this is what makes Callaway-Santana very different. Callaway-Santana doesn't need any of this stuff. Callaway-Santana needs literally one baseline untreated in order to estimate the average tree on the treated. You use the pre-treatment simply to do event studies to provide credibility for parallel trends. Synthetic control is totally different. You need long pre-treatments to get rid of the bias that is inside the method, okay? The idea is that if you're using a very short time series, you're fitting the model and you're fitting it off the error term, you're fitting it off the error term, not the factor loadings. So you have to get this long period of time so that these kind of transitory shocks, like both of these are going to look in the data. Neither one is observed, but this is noise and this is systematic. And so you're needing for you to have a long period of time so that, like, on average, that's 0. So it really can't fit on the noise. It can only fit on this, the true model. Okay. So the idea is that the shorter series is you're fitting noise, and probably not getting the synthetic control. You're getting a number, you're getting a set of weights, but it's probably not the synthetic control. So this is a paper that Manisha and I did, Manisha Shah. She's now at UC Berkeley, but she was at UCLA. She's one of my favorite people in the profession. She is going to be my 100th interview for the podcast. So I love her dearly and everything. You should read everything. We worked on this paper for 9 years, or rather, I discovered this natural experiment in 2009, rotor, and we started working on it. It was so much fun. It was really the highlight of my career in terms of like collaborating. She was just great. So this is what happened. In 1980, Rhode Island, which is, by the way, for those who don't live in the United States, Rhode Island is in the Northeast. It's a small state. It's near Boston. It's not a big state. And it in 1980, the General Assembly accidentally legalized indoor sex work. And it went completely unnoticed, unenforced for 23 years until a judge, a district court judge, ruled that, in fact, the state did not have any laws prohibiting indoor sex work. They had laws prohibiting street walking. They had laws that prohibited running a brothel. They had laws that prohibited pandering, which was having a pimp, but they did not have any laws prohibiting indoor sex work. And it's like they weren't really trying to legalize indoor sex work. That's like was the fascinating part of the story. They just reformed the law in a bad way, deleting awkward language, but not replacing it with more accurate language. And so the only language that was accurate, that was prohibitions on street walking. That was it. But in time, there was like a wave of Korean immigrants that moved after the IMF crisis in the 90s into Rhode Island, settled, and opened a bunch of massage parlors. And they ended up getting arrested regularly throughout the late 90s and early 2000s. They were getting arrested for street walking. No, post-treatment length does not have to be similarly long enough. All the fitting is off the pre. All the fitting is off the pre. Post is just imputation. All you really get from post is, I don't think so. No, I don't think so. There's no R squared or anything like that. I think they're pretty different. So here's what we did. So we had, this is our synthetic control, and we had about 0365. So that's almost 40 years pre-treatment data. And, the fit is not great. It's not great, not compared to GDP. The reason why, this is worth just kind of mentioning real quick. If you go back to, I'm just going to go back to it. I'm sorry. Cigarette smoking just does not change a lot over time. It's very smooth. It's very much it's very connected to cohorts. So, it doesn't really change a lot. It's not very volatile. Things that change a lot year to year are going to be hard to fit. That's what I learned the hard way. So rape, even when it's denominated per 100,000 in a small state, would fluctuate. we had some weird fluctuations. Secondly, Rhode Island, and I checked on this. I contacted the FBI. I contacted the state police that handled the Rhode Island data set. And I even called the statistician at the Providence Police Department. And each time I just said, are you positive that these data are correct? You know, that's one of the advantages with synthetic control is that it's one state. It provides a lot of things that you can do that you really can't do with like diff and diff, which is call people up on the phone, do tons and tons of research about one state. So there's a lot that you can learn that, it becomes practically impossible for 40 states that pass minimum wages or something. So the pretreatment fit's not great. The reason why we find anything is that this drop in reported rapes that happen is just completely unanticipated by this. But the thing is, Rhode Island is experiencing throughout this entire period of time rising reported rapes, and the rest of the country, starting around here, fell. So it was actually, very difficult to find. It's difficult, meaning like I've got projects like for that Texas project, everybody is experiencing rising imprisonment, and it's smooth pre-treatment. Already Rhode Island was an outlier. And so, this was like very hard to fit. And so, most of this is coming from just lagged values. And then we have our event study here. So synthetic control is going to do well when you have many time periods because you're not going to fit on the error term. Instead, you're going to find a synthetic control with the same exposure to the aggregate shocks. It's going to be matching on those factor loadings, but that does not guarantee that you're going to get a great fit. I don't actually know what other people's are getting, but to me, that's not nearly as good a fit as the other one. Okay. So this is what Abity says. Equation 2 can hold only if these outcomes and Z belong to the convex hull. In practice, it is often the case that there are no set of weights that will exist such that equation 2 holds exactly in the data. Then the synthetic control region is selected so that equation 2 holds approximately. In some cases, it may not even be possible to obtain a weighted combination of untreated units such that equation 3 holds approximately, meaning sometimes it won't even look good. Even with this minimization, it still may not look good, okay? This would be the case if it falls far from the convex hull of that. McDonald's, for instance, was falling far from the convex hull. Notice, however, that the magnitude of such a discrepancy can be calculated for each particular application. So for each application, the analyst can decide if the characteristics of the treated unit are sufficiently matched by the synthetic control. You can look at it. In some instances, the fit may be poor, and then we would not recommend using a synthetic control, okay? And that is the branching out of where this literature went. Are we going to give up on synthetic control if we cannot get a good fit? So Furman and Pinto have a 2021 article called Synthetic Controls with Imperfect Pretreatment Fit. They're both at the same school, San Paulo School of Economics. Extremely smart people. I did an interview with Chris Pinto. Highly encourage you to listen to it. She's wonderful. I have not been able to interview Bruno, but he's really cool. I like him too. So here's what they write. We analyze the properties of the synthetic control and related estimators when the pretreatment fit is imperfect. In this framework, we show that these estimators are generally biased if treatment assignment is correlated with unobserved confounders, which that's not terribly surprising. They're basically saying if you have omitted variable bias, meaning you've got a confounder that hits at the exact same time, as the treatment, it's going to be biased. We've sort of looked into this ourselves here. We looked at this ourselves and we were like, what if something is just happening in 2003? So in our paper, we did falsifications. We looked at all the crimes: murder, larceny, aggravated assault, grand theft auto, robbery, no effect on any of them. Only happens here, violence against women. So, that's one of the things you can sort of do generally. I'm a big believer, if those of you have my diff and diff class, I'm a big believer in trying to look for evidence of confounders. All right, but putting that aside, are generally biased if treatment assignment is correlated, even when the number of pre-treatment periods goes to infinity. Seems kind of obvious. It's almost incredible that it even needs commenting on. Okay. I one time wrote Abity back in like 2010, and I asked him, and I said, just to check my sanity on this, if I have another thing that happened in the year of the treatment, surely I can't say it's unbiased. And he said, yes, synthetic control assumed nothing else happened. So for our study, I mean, it's not easy when you do something like this, because you literally are just scratching your head and going, what else could be going on in 2003? What else could it be? So that's when I was calling the police, the chief of police. I was calling emergency room doctors. I was calling people that ran the like adult services newspaper, women's rights, women's shelters groups. I was really trying to figure out what even would the confounder be. And, it's like trying to prove a negative when you can't find it, but we were really trying to figure it out because this result was just so large. So here's what they say. Still, we show that a demeaned version of the method can improve in terms of bias and variance when you have that situation. Relative to the diff and diff estimator, we also derive a specification test for the demeaned synthetic control estimator in this setting with imperfect pre-treatment fit. Given our theoretical results, we provide practical guidance for applied researchers on how to justify the use of such estimators in empirical applications. So here's what they're doing. Big picture. You do your synthetic control, you go through, all right, and you've done 14 of these, and none of them look good, meaning none of them look good over here. They're doing all kinds of crazy stuff, okay? I mean, you could even imagine that one. Maybe that's a candidate, okay? We didn't quite demean, we did something else, but so we go Furman and Pinto, show that the synthetic control will generally be biased if treatment assignment is correlated with an unobserved confounder, even in very long pre-treatment time periods. This happens because the synthetic control weights are converging to weights that simultaneously attempt to match the factor loadings, that's the good news, and minimize the variance of a linear combination of the idiosyncratic shocks, which means it's fitting on the noise. Okay? None of this goes on in diff and diff. All right, so this is all uniquely the problems of synthetic control. Okay, so even if you have reconstructed the pre-trends, you may not have recovered the true weights. I mean, that's the thing to kind of remember. You're trying to get the true weights on that, and you need a comparison group so you would need a comparison group that was affected by the dynamic confounder in exactly the same way, just not yet treated. That's kind of the idea. So Furman and Pinto show that the synthetic control estimator converges to the parameter we want plus linear combinations of those shocks and the common factors. So if you assume these factors cancel out in large samples, then the bias is going to depend on the differences in how the treated units and the synthetic control units are being affected by those common shocks. They show that it is generally unbiased under the same conditions as diff and diff, They can have lower variance, but they recommend showing both diff and diff and d-mean synthetic control. I keep going back to my paper, but in our paper, we had to show diff and diffs and synthetic controls. In fact, in our paper, you might actually find this kind of interesting. I wonder if we have it. Submissions. Writing. Restud. AER. All right, let's see what they said. They did not like it. Let's see. They liked that it came down to a small number of annual data points for a very small state. And then they start kind of saying some random stuff. All three recommended reject. Okay, that was AER. Then I think we went to QJ first. Correct. You don't have to worry about simultaneous shocks. All you need is parallel trends. Yes. Is it? I think actually it's in the restud. Yeah, I think it's actually in the restud. We get rejected. All the reports say reject. It's a bummer. They all say go lower too. QJ Cat says go lower or along. So he's not crazy about it. He's not crazy about it. So then we go, okay, that's 2. Then we go to JPE. Same thing. JP submission. I don't even have the thing. So then we go to restud. And this, I want to show you what happened. So at JP, we got one accept or one revision R&R and 2 rejects. Here's what happens at restud. We were ready to quit all these top 5s. And I saw a YouTube video that restud had put out. And the YouTube video was interviewing people that had recently published, and all of the people that had recently published they were interviewing did applied quasi-experimental stuff. And because at the time, Restud was more known for doing structural and theory stuff and experiments. And so, you usually skipped it for people like us. But I was like, hey, I think we should try it. So, all right. Razvi Smet. Razvi Smet. Reject. Okay. Here we go. Oh, yeah, that's it. Well, okay. I was sorry I took that. So basically, we were told. I think I can show it. Let's see. If I go back to the QJE, let me show you how it originally was written. So this would have been 2014, I think, 2013. This is 4 years after the project got started. And I believe they did not like how long it was. Here. Synthetic control is the main results. We say, okay, diff and diff results. We go into synthetic control. But basically what happened was we were told to take the synthetic control results out. That's what we were told to do. They said, take it out by this one referee. And we were told, I was told in grad school that you can always disagree with the referee one time. So we disagreed. And what we did was we kept the synthetic control in, but we made it a robustness check. And so the diff and diff ends up being the main results. So we do diff and diff with randomization inference. This here is arrest, I think, arrest for prostitution. And, you know, technically the law change happens in 03. Back then, for some reason, I put the line between 03, 04. I wouldn't do that now. But that is technically a treated period. Falls. Now, there is this big increase in rape that happens in the year of the treatment. Then it falls. Okay. And then this is gonorrhea. So the demeaning, we don't demean in ours. We did something called smoothing because, you know, this was like 2013. So none of this stuff existed back then. But anyway, you cannot compare the original synth with the demean synth in terms of bias. If units were similar with similar factum loadings, had similar fixed effects, then matching on levels would be better than demeaning. So demeaning the data can increase the variance, but it can also decrease the bias. So demeaning implies extrapolating, which is often considered to be one of the hallmark strengths of the original synthetic control estimator, which does not extrapolate. So our Rhode Island paper began in 2009, published in 2018. Working papers 2014 was actually before. It was actually 2013 we submit. We'd been presenting for a long time, way before this imperfect literature. One of our main outcomes was reported female rape offenses per 100,000 measured in the uniform crime reports. Rhode Island is a small state. Even relatively modest changes year to year can cause pretty meaningful swings in the outcome. So it was our solution. We were really worried about the volatility of the outcome, so we smoothed it. It wasn't a demeaning though. So we didn't do this in order to do that, but we were trying to address the imperfect fit through smoothing. So that's how we handled it. But they talk about, Furman and Pinto talk about demeaning. So Furman and Pinto appear to start this literature on imperfect fit, and it continues. But what we're going to do now, all right, is we're going to examine not even with Furman and Pinto, they were still imposing it. Lygia says if the synthetic control estimates were also good, if the pre-treatment fit was good, well, I don't know. They're not really. You should go with the one for which you believe the assumptions are most credible. I would think if you have a very long pre-treatment time series, I would say if you had a very long pre-treatment time series, the believability of the factor model that you fit that model well, because you had a long pre-treatment time series, that'll probably always be, well, I don't know. I don't think it can be answered abstractly. I think a lot of the time you're going to probably find in a really great synthetic control. My hunch is you're going to find, my hunch is that parallel trends is probably holding at baseline. It only has to be at baseline for diff and diff. The parallel trends has to hold at baseline. your pre-trim plots might look good. Yeah, it's a long story. I'm not sure. I would probably say um report both for sure. Report both because 2% of the 2% of all MBR working papers are sent versus 25% of different of MBR is different diff. So that was one reason. We had a lot of referees in 2014 to 2018 that just clearly did not understand synthetic control and or did not like it. Synthetic control, the JASA had only been out for when we submitted in 2013, the JASA had only been out for 3 years. I remember us on the market presenting it and people just saying, take this synth out, just do diff and diff. And, we were like stubborn about it. Thankfully, Manisha and supported it. I mean, she agreed. So it just became a bit of a, being like early first movers on these methods requires a lot of confidence that you understand the methods, being able to explain them really well and defend it. And I felt like I had more confidence in myself. I had more confidence in the synth results with those long fitting of the pretreatment trends. That's how I felt. But yes, that's what I would say. If you had a long pretreatment time series. So we're now going to look at this relaxing of the convexity requirement. Convexity here, what it means is the weights had to be non-negative. The weights had to be non-negative. Okay. Now there was an earlier paper by a guy named Duchenko and Hito Embens, never gets published. A lot of the results in Duchenko and Embens get passed into the synthetic diff and diff paper, but it's out there. And one of the things they do in it, it's all about imperfect fit. And one of the things they do is they're like, look, maybe you can't get a perfect fit of Messi because he's such an outlier. But if you put in a constant intercept, then you could like shift the synthetic control up and down. And even though it's not a synthetic Messi, it's like a synthetic Messi -2. And then, you could just sort of you have it be really similar just below it. That was the idea. Now, in that sense, it was had a little bit of some attributes like diff and diff a little bit. But we're going to look at one that went a different route. We're going to look at one that used negative weights. This is the augmented synthetic control paper. I have lost track of time. So we're going to take a 15-minute break now because I definitely feel like we're close. So we're going to come back 47, 53, 52, 52 minutes on the hour. All right, we'll come back at 52 minutes on the hour. And I'll see you in a second. We'll start augmented synthetic control, which will wrap up the day. And we're doing good. All right, so we'll be right back. We'll see how far we can get. We're going to be doing yeah, so we're going to be doing a couple of things. Let me see here. We're doing the augmented synthetic control here. I think that, yeah, here we go. All right, I'll look at that in a minute. So we're going to be doing this command here called augmented synthetic control. And it's this one is what we're going to be doing. This is augSynth_prison. And here, Causal Inference 3, Labs, Texas, R, augSynth. It's this one. I don't know what that is. Okay. Oh, that's the okay. So we're gonna be running that. in just a minute, we're going to see how to use the aug-cent command to run the original ABITY, getting these jackknife confidence intervals. You could not get the confidence intervals with the original, or he didn't provide that in the original. Then we'll look at augmented cent with control without covariates. Okay. And then we'll put in covariates. Right. But I believe that everything has got to use all of the pre-treatment data. So we're going to be learning this method. Right. So everything that we've done, just to kind of summarize it real quick, so far, weights have all been non-negative, right? They've all been non-negative. They've been the vector, the weight, the W vector has been sparse too. A lot of zeros, a few positive weights, right? That's what's been going on so far. Okay. So, and that's because that is not because no, I don't, Tanisha. I don't think it is even, you remind me in a minute, Tanisha, I don't think it's available, but it might be, but I have not seen it in Stata. Yeah, this is part of I wrote a Substack a little bit about that recently, Betty. Where, this like these firewalls where stuff's getting written in one but not another, has been a little frustrating for many of us that have sort of a lot of human capital built up in one of the three, Python, Stata, and R. And there's some people that'll do all three, and then there's, and then it's, it's a lot of work to get it created in all three. And I completely understand. But I don't think so. But I'll check. We'll check. We'll do a Google search. But here's the deal. So synthetic control estimates the optimal weights, but it's a constrained minimization problem. So they're not optimal globally. They're, they're optimal conditional on those weights being non-negative, okay, and summing to one. That gives us a convex hull constraint and ensures that synthetic control is a feasible counterfactual in that it is going to be formed by a combination of control units that are, similar. It's like a matching principle. Okay, it's like a matching principle. When you go back into like the unconfoundedness literature, which is like regressions, matching, propensity scores. Okay. There's basically like two ways that you could kind of think about that literature. One of them is the matching weighting methods. Okay. And the matching weighting methods use similar units as controls. Then you've got the regression methods. And they extrapolate. They extrapolate using functional forms. Okay? Using functional forms. They don't need to use, units that have similar like they don't have to have like, this is why when you learn your regression, when you learn regression in your econometrics class the very first time, you didn't ever hear anybody talk about like, oh, look at make sure that the covariates are similar in each group. Do we have overlap? You never really learned that. You just learned about exogeneity, and you knew that the minimizing that OLS did to find those coefficients would equal this parameter. But what it was doing was it was extrapolating to estimate those potential outcomes using the functional form. Okay. So synthetic control is basically Abity synth is really over here. It's kind of like this one. And then augmented synth is more like this one. It's more like this one because it's not going to be, it's like augmented synth is going to be used in a situation where you can't find similar units. Okay, that's what you're going to be doing is you're going to be using augmented synthetic control in a world where you're still working with that one, or at least it's an option. It's an option for you to use it because you cannot satisfy anybody with a pair of eyes that you have weights, a vector of weights that is reproducing the time path of the treated unit over a big chunk of time. Okay. In which case you go, all right, why can't I? And the reason you can't is because of those positive weights. Positive weights are in the synthetic control. Positive weights are forcing you to use similar units. That's what's doing it. Okay, that's what's doing it. And if the best you can do with positive weights is not to do a very good job, the question becomes, do you give up or do you relax it? So over here is the introduction of some negative weights. They're going to allow for some negative weighting. Okay. And the way that I think about it, the way I may not have this in here. No, I don't have it in here. So the way that I think about it is, if I have to generate a synthetic Messi, when he is arguably, let's just say, he's arguably the greatest of all time, right? On some dimension, he's untouchable. All right, if I have to generate a synthetic Messi when he is arguably the greatest over time using non-negative weights, then I will under the best case scenario, my synthetic Messi will using the best players in the world still will not look like Messi. And the reason is, in order to look like Messi, like this would be Messi. You got to have better players, and you got to have slightly worse players. Because what you've got to do is Messi has to be equal to, weighted 1, player 1, plus weight 2, player 2, plus weight 3, player 3, plus ... plus weight K or N, player N. Like you've got to have all of that. And the weights, W1, W2, W3, W2, W3, ... Wn has to sum to 1. So, you've got to be able to basically have him be in the middle. Synthetic control in the original with the non-negative weights, synthetic control with non-negative weights is almost designed for average players. Because it's got to be in the middle. You got to have people above and below. So, it's not designed for these extreme groups because by definition, the extreme groups, you can't take a weighted average of other players. If the weights are fractions, you can't take a weighted average in order to get them. But you could take a negative weight. And when you are negatively weighting, all right, this is how I kind of an analogy, the negative weighting allows you to use worse players whose bad playing when negatively weighted looks like Messi's amazing plays. That's the idea. It's a real, like, you know, that's the whole thing, is it does not fit over here with this with the kind of historical matching methods that are used. It doesn't really fit over here with the spirit of find units that are similar. Find units that are similar. Over here, when you put in negative weights, you're extrapolating based on the model. It's a model-driven extrapolation. You've got to have a lot of confidence in that model, that it has the ability to do some kind of extreme, well, you don't want it to do too extreme, but it's doing some sort of, you know, extrapolation based off a model, because you can't find anybody similar. So it's like augmented synthetic control is going to be somewhere in between. It's going to be somewhere in between what Abity is doing and like a fully unconstrained model that allows the weights to be, you know, whatever negative that they want to be. Okay. So it's going to be this, it's going to be basically the least negative weights. All right. So Eli Ben Michael, Avi Feller, and Jesse Rothstein present a modification to Abity, Diamond, and Amuler. And I think my slides actually are a little bit overwritten, so I might skip some. I keep meaning, I noticed when I made this, I maybe overwrit it a little bit, but they allow for negative weights, just the least amount of negativity that is required in order to get to the convex hull. Okay. What they're going to do is they're going to augment the original synthetic control there's a lot of stuff going on in this paper. They're going to augment the original synthetic control model by adjusting for pre-treatment imbalance using doubly robust bias adjustment. For those of you that took my synthetic control, or sorry, my causal inference 1 class, they're going to incorporate Abity and Embin's 2011 bias adjustment or bias correction method with nearest neighbor matching. They're going to estimate the bias and then use it to adjust for that imbalance. Okay. And this augmentation that they're going to be doing, they say it's conservative negative weighting using penalized ridge regression. The constraints in this regression are such that the negative weighting that they are allowing, it's not the negative weighting that would be like best. It's the negative weighting that is necessary and sufficient to get to the very edge of this convex messy. Like it doesn't, the negative weighting is not going to shoot you to the middle. It's going to shoot you to the edge. It's like you should literally imagine like a circle. Okay. It's like literally imagine like that this is the convex hull. And this is the best your synth can do right here. Okay. This is synthetic messy using non-negative weights. It's the best you can do. You could have a certain amount of negative weighting that took you right to the middle. And like maybe something like lasso might do that. Or you just go there. Okay. You're going to do the least amount of augmenting that is necessary in order to achieve unbiasedness. So it's like these kinds of methods, you know, these kinds of like regression-based methods, all right, they are not trying to do causal inference. What are they doing? They are trying to minimize mean squared error. Okay, that's what they're trying to do. They're trying to minimize mean squared error. And to minimize mean squared error, they're going to go as far, they're going to fit that data perfectly. All right. We're not trying to do that. We are trying to estimate the counterfactual. And to estimate the counterfactual in this framework needs only to go to the edge. And that's what they're going to do with this penalized ridge regression. Okay. So they're not going to overweight it. So this is where I start being a little bit redundant, and I apologize. So original synth needs perfect fit, means in practice it's going to be biased, as it won't be the case that we get constraints, weights that puts us on the convex hull. Like I right here, this is that is not perfect fit. All right, that's not perfect fit. So redoing that paper with augmented synthetic control would be low-hanging fruit, for somebody to do. So we don't do it. So anyway, constraint such that, all right, what did I say? So here, original synth will be biased in practical settings, as it won't be the case. We get weights constrained, be on the convex hull. Augmentation is going to use an outcome model. And this falls literally almost verbatim from this old paper. They're going to use an outcome model. Outcome model means a regression model, right? They're going to estimate the bias caused by what they're calling covariate imbalance. But remember, the covariates are the covariate imbalance includes the lagged outcome. So you've basically got the reason why you have bias in this framework is because you've got bad matches. That's in these frameworks. That's what's going on is that you have a bad match. But bad matches have bias associated with them, and that bias has certain forms. So they're going to estimate the bias and then just delete it. And in that process of deleting it, this outcome model is going to be a ridge model, and it's going to provide new weights. When they do this outcome model, it will generate new weights. And what they're going to do when they generate these new weights is they're going to take the original synthetic control, which is biased, okay? They're going to re-weight it. And in that re-weighting, it will introduce negative weights. It's just that it's the least negative that has to do to get rid of the bias, okay? When synth is imbalanced, augmented synth will reduce the bias by re-weighting. All right. It's just and that sounds like, so when you hear that, most people, I think, would say, if I said, if synthetic control is imbalanced, and imbalanced just again means in our paper, that's imbalanced because the covariates are not balanced right there. So, and we tried to get them balanced. We couldn't. So when it's imbalanced, augmented synthetic control will be less biased, but it only does it by introducing negative weights. So there's no free lunch with it. If your whole point is, I do not want to be extrapolating, I want to be using units that are similar, well, if it's imbalanced, then you can't even answer the question. So you're going to have to make some hard decisions if you even agree with Abity in the first place. If you really are indifferent and you don't mind that kind of, extrapolating, then you're fine. So when synth is imbalanced, you use augmented synth that reduces it. When synth is balanced, literally augmented synthetic control is the identical estimator. So augmented synth always reduces the bias. It just does it through the negative weighting. All right. And they even argue that synthetic diff and diff can be seen as a special case of augmented synthetic control. But this paper came out before the published synthetic diff and diff. So I've not really seen anybody try to respond to that. So here we go. You have J+1 units. It's the same notation. J+1 units. Unit 1's gonna be treated at some period, and you're gonna have a donor pool units of never treated units, not the not yet treated. They're never. Is D? Well, they're never for the panel length. They can be 1 day treated, but for the panel length, they have to never be treated because you're going to use them. They're going to be functioning as the synthetic in the post-treatment, and you can't be having them get treated. And then the treatment indicator is a D, and once you're treated, you're always treated. Ta, I see you typing, so when I see you hit enter, I'll say it. Okay. Ta says, is there like a falsification? That's a good question. I mean, if you do. Maybe. It's a good question. Trying to think through my mind. If they're different, I think if you did augmented synthetic control and the original synthetic control, and they are very different from each other, it would suggest that synthetic control had imperfect fit. Because when they are identical, when there is no imperfect fit, they are identical. So if there is imbalance, then augmented synth will always be different, in which case, now I don't know if you can quantify the bias that way. I don't know if that, because you don't still know, you still, I'm not positive you can if you can quantify the bias. Just off the top of my head, I'm not positive. But I think I would probably feel comfortable saying, since they are identical with perfect fit, then the only explanation when they are dissimilar is that synthetic control had covariate imbalance. Although that's also visible too. That's something you can test to see that, the original, I mean, like like I was doing here. I mean, you can tell that's different. Okay. Pre-treatment outcomes. It's a model of 2x2 single. So in these papers by these newer papers, they talk a lot about the block structure. We'll talk about it again tomorrow. The block structure and the matrix gets a lot more discussion than you're used to, especially in diff and diff, or even in the original synth. So this is a model of a 2x2 where it's a single last period block structure, not a staggered rollout. Last column is always post-treatment, switches from Y1 to Y0. So here we're going to have our treated unit. Here's our control units. Okay, they're untreated. All right. So synthetic control, their notation's slightly different, but it's really the same thing. First of all, look at this. There's our weights. Weights are summing to 1 and they're non-negative. Now you do see this thing right here, this penalization on this. So we're going to minimize, again, it's minimizing this norm. And we said, the form of the norm that we were looking at was the V times the discrepancy gap squared plus V times the discrepancy gap of a different covariate squared up to all the covariates, where it was the pre-treatment characteristics. And we were solving for W that minimized it. Now they're going to put this like penalty term on here, but they basically are going to make a little statement. All right, and I'll get to it in a second. The way we learned it, was that wasn't there. It was just minimize this distance function, minimize it, the sum of all of them squared, subject to that. And now all of a sudden, for the first time, we're seeing this, penalized regression. And we are hoping that Y0 hat, which has been being estimated with this control group units times W star, we're hoping that this is all the control group units multiplied by the optimal weights equals the counterfactual Y0 for the treatment unit. That's what you're just hoping that it does based on a perfect fit, which is not going to hold. Here's the V matrix. A lot of this is redundant. Vx is the importance matrix on X0. State of default chooses Vx that minimizes mean pretreatment, mean squared error. All right. The modification that we noticed right here is the inclusion of a penalty term, but it's irrelevant. The choice of the penalty is less central when weights have these constraints because it can't really do anything. What's going to happen is that this is going to start to matter when we relax this part right here. That's what's going to make this penalty term start to pick up. So These weights will be used. So when we minimize this, these weights are going to be used to address the imbalance, right? Not the control units. Okay. So synthetic control is here. Synthetic control is here. The weights that we are going to be estimating are the weights that are going to be applied to delete the selection bias. The selection bias, I call it selection bias, but the bias associated with the covariate imbalance. Okay. All right. Because this method is for, that's because these weights are going to get you as close as possible to the convex hull, meaning like this weighted average, group of players is as close as you can get to messy, but it's still far away. All right. So that's done. Once that's done, it's done. This part will then redo it. It's going to now reweight those W's. So it's a separate procedure coming in right here. Okay. So we have this original factor model. We know that this is the bias. Bias requires that the ratio of the error term to the number of pretreatment periods is small. Okay. The bias of ADH requires perfect fit using their factor model. And that's just another way of saying that the units that look alike, and on observables, which is what you matched on, and the unobservables, which you cannot match on, only those that look alike over a long period of time have you probably, matched on the unobservables. Your weights have correctly approximated the factor loadings on those unobservables. Otherwise, the argument is it would not have followed that long trajectory. And this is from 2015. I'm not going to read it. Well, applicability of this method requires a sizable, I do need to read it. So this is just a reinforcement. The applicability of Abity, Diamond, and Haymuller 2010 method requires a bunch of pre-intervention periods. The reason is that the credibility of a synthetic control depends on how well it tracks treated units' characteristics and outcomes over an extended period of time prior to the treatment. There's a lot of covariate balancing that you should be doing. There's a lot of balancing, or there's a lot of checks that you should be doing on this. We do not recommend using this method for two reasons. If the pretreatment fit is poor, or the number of pretreatment periods is small, which to everybody always asks, well, what's poor and what's small? And, just like he doesn't say, all right? So a sizable number of post-intervention periods may also be required. This came up a minute ago. A sizable number of post-intervention periods may also be required when the effect of the intervention emerges gradually after the intervention or changes over time. I think somebody was asking about RD and time. So like you need a number of post-intervention periods if it's a gradual change. And so like in this example, it doesn't just like immediately happen. If you did there, there is definitely a big jump right there, but like, it's, you need a few kind of get it, Okay. So here's the outcome model. Assume that our outcome Y0 follows that factor model where M is all the pre-treatment potential outcomes. M is going to estimate the post-treatment outcome. And so it's going to be a measure of the matching bias. So the procedure, and if you're not familiar with this paper, then just know that we do things like they're borrowing from a paper by Abity 2011 to propose a bias correction off of an outcome regression model. So Abity, Furman, they say the same point as T grows, synthetic control achieves balance. And it achieves balance in the large pretreatment, not because it fit on the noise, but because it fit on the heterogeneity in the factor model. Thus, when the weights do get exact balance, the bias of synthetic control decreases with T. It's just that in a finite sample, you're not going to get it large enough. Okay, so usually the number of time periods isn't much larger than the number of units. So like we look at my problem here, it's like, oh gosh, I cannot stand the cat stuff. We have 51 states. And I have, 15 years, 16 years, So usually the number of time periods isn't much larger than the number of units. Mine's not even as large. In my project with Manisha, when we go back to this, what did I have? 2003 to 1965, I had about 40 years and I had 50 states. Still not, I don't even know. I mean, I honestly don't even know why they said that. I've literally never seen a study that had more years than state units. And yet the thing is the asymptotics is all about T going to infinity. And usually you don't have as many units. Your units are bigger than your T. Okay. All right. So exact balance rarely holds. Which if it doesn't hold, then the unobserved heterogeneity doesn't get deleted. So here's the illustration. I already kind of drew this. There's the convex hull. That's what you're looking for. Basically, a weighted average of the units looks like the treated units. Here's the messy situation. Got a best case scenario of the best players, weighted average, and they still do not look like him. They might play like him in trends, but in levels, they won't do it. So what we're trying to do with augmented synth is to get to the edge. That's the graphical explanation. All right, so how do we do it? We get to the edge through the reweighting. So we're going to adjust the synthetic control. We're still going to estimate the same synthetic control model. All right, we're still estimating the same synthetic control model. It's a second step that tries to estimate the matching bias. Okay, so we're going to use our outcome regression model to estimate the post-treatment potential outcome for those units, which recall is unobserved for the treatment group, but which is observed for the control group. Okay, this is Y0J T. We're going to use our regression model to predict Y0 in the post-treatment, and then we're going to use that to then get estimates up with that model, then get estimates of the matching bias for both. So in other words, there's going to be two steps. Estimate synthetic control using optimal donor pool weights, all the stuff we spent all day on. And then second step, estimate the matching bias using ridge regression, go back to this and adjust it, similar to that bias correction. All right, so this is going to be like so Y1 is the augmented potential outcome based on synthetic control. Here's the first term. That's our synthetic control. I'm going to put stuff in like this is synthetic control right there, right? Synthetic control is going to have matching imbalance though. So if I take this and I subtract, if I say the true Y1 minus this weighted, it's not going to be a 0. So it's got some imbalance. So then what I've got is adjustments for the matching imbalance. And that's the form right there of the bias adjustment from this is the same form of the bias correction in nearest neighbor matching in that Abity and Imbens 2011. What they do in that paper is they they estimate with a regression model, they'll use only the donor pool units. They'll estimate the regression model using the donor pool units. They'll get a predicted Y0 off of a bunch of coefficient estimates, and they'll get predicted Y0 for the treatment group and the control group. And that's like the technique. Well, that's what they're doing here too. That's what they're doing here too. Except they're doing it all in the context of like synthetic control, not in the matching context. All right, so they're going to get this predicted Y0. That's what this M is. If you look back, M to estimate the post-treatment potential outcome, right? They're going to get this regression model to predict Y0 in the post-treatment period, but like it's observed. Y0 is observed for the control group. So they're going to predict it, and then they're going to use that prediction to correct. Then they just rearrange. But look, if there is no bias, right, then those two things are the same. It's when they're different from each other that it's biased. So if there is no bias, then the prediction of the bias for the treatment, the prediction of Y0, see, like the post-treatment Y0 for the control group is supposed to be the post-treatment Y0 for the treatment group. That's what synthetic control is. This right here, that right there, that's supposed to be the truth. That's supposed to be what would have happened had this event not happened to this unit. Okay? So if it's a perfect fit, then there's no bias. And that means whatever you got for the bias here, well, this is the bias, but like the difference is the bias. But whatever you got for this, and then you got for this, if it's the same, it cancels out, in which case augmented synth is just the synthetic control. So this right here is just the bias. Like this is the bias that you're at. This is the bias correction. Then it gets like redrawn. So they just like move some stuff around. I'll just do it since it's fun to do. So here, that's going to go there. What's going to happen now? What's going to happen now is what? This is this. Okay, is got a W hat J here in common. Okay, so it's going to pull that out because they both have the summation sign. It's going to pull it out. And so then it's going to be the weight from the synthetic control weight times my synthetic control. That right there is my synthetic control minus my bias. That's my like synthetic control minus my like predicted bias on it. Okay. From my outcome regression. It's a lot easier to explain this if you've seen the Abity and Nimbus thing, and you can so clean there. But anyway, the first line in the traditional synthetic control weighted outcomes are corrected by the imbalance in a particular function. They're getting corrected. So like if this was if this is not equal to it, then that's the bias. And so they just basically estimate the bias, delete it off. They just delete it right off. If the bias is small, that's a teeny tiny number, okay? Then it means basically that minus that is the same thing, goes away, and so augmented synth is just that synthetic control. Okay. So how do you do it? To estimate, so that's what you got to do. So the question is, where am I getting that? Where do I get it? The adjustment is straightforward. Where do I get it from? All right, it's an extrapolation of Y0 based on covariates. Ugh. These cats, they just are all over me. They just put hair all over me. Based on covariates. I mean, I created that problem by having 4 of them, so you can't really complain. To estimate M hat, recall what you're doing. You are basically, I mean, it's like this. It's like this. You know, y regress onto a constant, beta x, you know, gamma z plus error, right? You like for the controls only, for the control group only. You then get a hat, beta hat, gamma hat, and then to predict y hat. It actually becomes y0 hat because it's the control group. So it's extrapolating off of a form like this. Okay, that's what's going on. All right, based on these covariates, but it can have overfitting problems when you do this. So the original Abedian embeds, they don't do any kind of like addressing of overfitting. So, but they're going to do it. They're going to address it by introducing a ridge regression. And the hyperparameter, they're going to suggest cross-validation. And it's inside this second, like run a outcome regression model, Y0, with this ridge regression. And so the second reweighting, which they're calling bias adjustment, that the negative weighting comes in. And it comes from the outcome model itself extrapolating, because extrapolating is always does that kind of negative weighting. So here's the ridge. Y minus, you know, this eta 0, x, minimize it, squared, plus this penalty term. We're going to estimate m hat with ridge regularized linear model. Penalty parameter lambda. It's unfortunate that it's lambda because Abedi used lambda. It's not the same lambda. But once we have these, we'll adjust for the imbalance using the ridge parameter as a weight on the outcome model. All right, so here we go. There's set. Now, what did we have before? We had that m hat right there. Okay, so we had, I'm just gonna look at that again. We had, this is the same. That's the same. Yeah, that's the same. So we got m hat 1t minus weighted minus the cent m hat. So this is going to be x1, which is the inputs used for the prediction model, minus weighted x times the ridge itself. This is our outcome model here. And this whole thing, all of that is augmented synthetic control, and that is the weight augmented synthetic control with the bias adjustment, and some of the weights are going to be negative. That's the only way to do it. The only way to get that any improvement is that reweighting, because like this already is optimal. It's just that just because it's optimal doesn't mean that it fit, you know. So the only way you're going to get it any better is to allow some of those negativities to come in. So you can achieve better balance, but it comes at a cost, higher variance, and can introduce negative weights. We're kind of trading off the bias for the variance a little bit. This is where I started kind of being a little bit redundant. I feel like I've already said all this stuff. So here we go. So this is the intuition. Ridge begins at the center, but ridge augmented synthetic control begins at the cent solution. So if we had just used ridge or just used lasso or something like that, it'll always kind of go too far. It'll negatively weight too much. This is synthetic control. Okay. And we're just going to kind of move it a little bit to the synthetic control. Inference in this case is based on a paper by Viktor Chernyshkov and several others, which I believe I put in the paper. So there's this thing called conformal inference that he does. Let's see. Now, what's cool about this one, let me show you what's cool about this one, is that they replicate our paper and we survived it. They looked at gonorrhea. revisit the analysis. I was so relieved. Anyway, so what is it we're going to do? So here, I'll just read the, let me read the thing here. We introduced new inference procedures. Whoops. We introduced new inference procedures for counterfactual and synthetic control methods for policy evaluation. So this is the alternative to that Fisher method. Okay. Let me see. I got a chat here. What is, Charles, remind me what compound treatment means? Is that being treated more than once? Because we're assuming one treatment. Well, one thing that I'm not sure if you can see this. One thing that we are gonna have to we are always assuming SUTVA. SUTVA has here two things that we're thinking about: no spillovers / no interference between the treated units and the potential outcomes of the donor pool unit. So the donor pool unit are their own, everybody's treatment status is based on their treatment status. Like their potential outcome switching from Y0 to Y1 is because they were treated. So in that sense, there is no interference. That is something we're going to have to think about. Okay. So, it depends upon the treatment, but you might have to drop, you might have to make a donut or something around your unit of interest. And then the other violation of SUTVA is if there is hidden variation in the treatment, which that might mean what compounding treatments are, but hidden variation in the treatment means like, that the units, that the definition of the treatment is different per unit. Now, if it means compound over time, that might mean that there are multiple treatments, in which case that is, you're right, that this is assuming I mean, I think maybe, but actually, Charles, it might be, if it gets treated in 95 and then it gets retreated in 97, it very well, yeah, I think that's complicated. I don't have a comment on that. Those guys have those arguments, and I just don't. I don't. That one in particular, I don't really get into. I mean, I do think that my brain works best if I can imagine running a randomized experiment. I think I probably do have that, deep down inside me. The design tradition imagines that the treatment is varying because of somebody varying it. So you have to, so, in that sense, I am kind of sympathetic, but I'm very, don't feel confident enough to say I would disagree with Pearl. So we recast this causal inference problem as a counterfactual prediction. Structural breaks testing problems allows us to exploit insights from conformal prediction. Structural breaks testing to develop permutation inference procedures that accommodate modern high-dimensional estimators, are valid under weak and easy to verify conditions, and are provably robust against misspecification. All right. So that's what's going to be used. They also going to use a jackknife. So you're going to choose a sharp null. I'm not going to go at the steps to conformal. So here we go. They're going to examine the performance of synth against a bunch of stuff, including the demeaned thing from Furman and Pinto. So here we go. We're going to go synth, Abade's synthetic control, against Ridge, which remember Ridge is doing this, going right into the middle. over negatizing, if that's such a thing. Augmented synth, that's the one, the ASR is the one that we're looking at. That's Bruno and Furman, and then this is like a two-way fixed effects. And so then they're going to do it under, 4 different data generating processes. And what they're going to find is that augmented synth with a ridge outcome regression reduces the bias relative to synth alone every time in those 4 simulations. And so it underscores a couple of things. Abity, that's what they say, Abity's recommendation to use synth in settings with excellent pretreatment fit is correct, because this kind of fits Taha's question, because when they use it, when there is not good pretreatment fit, they get different results. They're going to look at a Kansas tax cut. So they're going to go Abity, Ridge. I don't know where the D mean goes, but they're going to go Abity, Ridge, which is the one we've studied. Ridge, we did not really talk about this. Ridge with covariates. Ridge with covariates residualized, where they residualize the covariates. And you can sort of see a little bit that with the reweighting, now right there and there, well, over here, let's just focus on these two since it's the only one we studied. It looks like it is smoothing it out a little bit. That gets improved a little bit. That looks like mine. And in this case, when it improves it, they're finding a little bit more of an effect. The confidence intervals are only on the post-treatment. So they're only putting confidence intervals on the treatment effects themselves, not these leads, okay? Here's what the lagged outcomes only, all right? And so look, here's the sparseness of the traditional Abity, bunch of zeros. 1, 2, 3, 4, 5. Only 6 states have non-negative weights. And with this ridge augmented synth, well, probably nothing was 0. Okay. But basically, they're like pretty similar. They're not too similar, but it's like some of this stuff is getting a little bit of, it's just tweaking it a little bit with those negative weighting. So the hyperparameter is chosen using cross-validation. You can put in covariates, but the default uses all lagged outcomes, which is not what we were doing. Okay. So in conclusion, synth is best when pretreatment fit is excellent. Otherwise, it is biased. You can reduce the bias if you're willing to have an outcome regression model that estimates the bias through extrapolation and then deletes. That deleting happens through this reweighting method. And that reweighting method, it's basically a reweighting of that. So ridge regression augmentation, it will, and it's not literally that you can't, if you multiply something by 0, it's still 0. So what the reweighting is doing is, it's literally all of that. All of that is the reweighted. So you got your synth in there plus this, and they can sort of re-express it, summarizing it all together as the weights. Sorry. All right. So synthetic control avoids it. All right. So here we go. Ridge regression will allow for a degree of it to achieve pre-treatment balance that creates negative weights, and it will dominate it in those instances by extrapolating outside the hull. All right. So let's look at this in action. Tomorrow is what we're going to work on. Let's look at this in action. Okay. So we're going to go over here to our studio. So we're going to go augment prison. All right. So we're going to pull up. I'm going to clean this up. Okay. So we got to install a bunch of stuff. This is the big one. And you also need all these SC tools. So let's pull that in. I messed something up. Feels like every time I use this, enter one or more numbers. Not that I know of. Ah, Abdi and Lahore. Hmm. Says it's in here. It might be. It might be. Um, it's not. Maybe it's calling it something like negative weighting. It automates the implementation. All right. So the extensions are bias corrected synthetic control gaps to adjust for discrepancy and predictor variable values proposed by Abdi and Lahore. Yeah. So it is doing it. Okay. I'd have to really dig into this, but let's put this in the chat. Okay. And then also put it into Discord. Okay. So we'll put that there. And let's see if I manage to get this R thing to run. Okay, good. All right, it did it. So we're going to read the data in here. Okay. So it's treated after year 1993, or if it's in 1993. All right, so now we're going to do synthetic control. Now, it's a little weird. It's a little weird because all right, so I'm going to do synthetic control Abity. Okay, the weights are right there. And I don't know exactly how to interpret some of these weights because they should not be negative. But if you remember, augmented synth did put a little bit of a penalty term on it. So we're going to go aug synth, BMP prison, treated. It's going to use all the lags for the controls. State FIP year, Texas. Prog func, I say nothing. S synthetic control equal to T. I'm going to run that and I'm going to list my weights. And that's what I don't really understand. I just there are negative weights. It's a negative. But look, see, they're like practically zero. So I don't really know. I don't really know what to think of that. 1, 2, 3, 4, 5, 6, 7, 8, 9. So, here's one that's 0.03. So there's like all these nines and tens are just small numbers. There's a few big ones. Anyway, so I actually wrote Ben Michael and asked him, and he didn't really say a lot. So we're going to summarize this. All right. So here are our estimates. And remember, this is pretty similar to what we were finding. We go back to, this part right here. 23 was like, this 23 is like right there or something. 7,500. I'm finding 60, 75. It's a little smaller, actually. It's smaller effects. 94, 10,000. Yeah, now that's similar. That's pretty. Oh no, 5,000. So yeah, who knows what that is? Oh, that seems like that's anyway. So 94, that's a little bit over 10,000. So it's smaller. Okay. Now I'm doing the conformal inference. This conformal inference is consistently just gigantic. You'll see it. And I don't know what to do with that, but here we're finding pretty similar effects. If we plot it, I'll show you what the conformal inference looks like. Huge confidence intervals. It's something that happens with my data. Here's the jackknife. Here's the jackknife that has those confidence intervals. Now we can do no covariates, synthetic control. You change the prog function. You can choose between ridge, elastic, net, but ridge is the one we learned. So we're going to run that. We're going to use the cross-validation to cross-validation here, right? And we're going to save. So we're going to list those weights. Okay, we can get weights that way. We're going to summarize it, get our ATTs. So with the covariates, didn't really change it very much. What did I put in as controls? Oh, that's still no covariates. Got it. Oh yeah, this is rich. So it's not changing it a ton. We'll do this one. So the jackknife. So it's not changing it a lot. Well, I don't know. We only have one outcome and we only have one treatment time. So not really sure why that would be a problem. Maybe this aug scent can handle multiple treated units, and I didn't know it. Here we're gonna put in some covariates. A couple of these are gonna matter. Much bigger effects. Look, so we find in the first year 3,200. If you look back to what we were finding before, it was much smaller. Finding much bigger effects when we put these covariates in, but they stabilize to the same number. We do the jackknife. Okay, so and if I look at Texent or if I do this, there's also a synthetic control with lasso, but yeah. Okay. So the only thing I think we probably would do yeah, I think so, Winchin. I think so. I think that's right. I mean, we knew there was a little bit of some imbalance in this. We knew there was some, right? Like we were off by what was it? 1,700 black male prisoners or something, 1,200, 1,200, 1,300. So we knew it was a little bit off. So it was a little bit. And so the results are pretty similar. And then when we put in these covariates, I mean, you know, I don't want to check. Let's see. So if we went here. So here it's like 1993, it's 3,200. So Abity finds 1,400. So when I put in covariates, I'm getting 3,200. 94, I'm finding 11,000. It's getting pretty similar. They're similar, right? They're definitely similar. They definitely seem to be at the farthest end, 99. They're pretty close. It's off by about 1,000 though. That's, nothing. 27,000. They're off by 1,000. So they're getting pretty close. This is without the covariates. When we did the augmented synthetic control here. Wonder how similar it was. So 93, 14. See, it's not exactly the same. It's really not exactly the same as Abity and Invens. Sorry, as Abity. Oh, well, you know what though? I don't know why I'm saying that. Their model right here uses every single lagged outcome. And I don't do that. I use 4 lagged outcomes and covariates. So I forgot about that. So it's not, I would need to just do all lagged outcomes and then compare it. But that's when you're getting with augmented synth is that these canned augmented synth, it'll let you put covariates in, but it's going to always use all of the lags. Whereas when we were working with this, you could pick, but you're kind of cherry picking a little bit. But what you could do is you could do those 14 specifications. But once you move into augmented synth, I don't know if you can do those 14 specifications. You just can do the all. You can do all with covariates, but that's it. So probably like to summarize this, if I can summarize it, what I would probably say is that this is a method you would use if you felt that the pretreatment fit was not great. If the pretreatment fit was pretty good and you didn't want to extrapolate, you wouldn't have to do it. But I mean, I'm kind of always of the opinion that that augmented synth in that situation might be more like a robustness check, where you could sort of say, even with a little bit of negative weighting, here's my results. And what you would basically be doing is probably, I don't exactly know how I would visualize this, but you can sort of see here that you do have the ability, 93, you do have the ability to at least check that, yourself. And I would probably say, in the short run, there is a bit of a difference, and in the medium run, there's none. By the time we get to 94, it's really pretty similar. That's pretty interesting. So sometimes, it might matter, but technically, what this means is that pre-treatment fit here that was not great, that pre-treatment fit that was not great right here, we've now reduced the bias of it, but we did it through outcome regression extrapolation. Okay. All right. So that's a long day. We didn't do too much though. We did a lot of just, I mean, if I could just summarize, we did Abity. I think hopefully if you were able to hang with that, you feel like you understand what Abity's model is basically about. We spent a long time in code. We looked at 3 different, models for doing it. And I kind of pointed you to a Python package also. And then what we did, we really emphasized that, synthetic control really needs to have good pretreatment fit. And an early method that tried to address the imperfect fit was Bruno Furman and Chris Pinto's just simple demeaning. Still uses, yeah, Eduardo, it's going to be the visualization. It's going to be the visualization. And also you could do both of them. You could do both of them. And if you find results that are very, very different, it does suggest that you had big improvements come from the negative weighting. But yeah, I would say that the pre-fit tests have always been very visual. They've always been very visual. So we have here so you got basically the perfect fit, but putting aside perfect fit, we learned the technique. It's the minimizing of the sum of the squared matching discrepancies. There is that V matrix on it, but putting that aside, that's all it was. It was a unique solution. It was optimal in the sense that that one vector gave you the smallest sum of the matching discrepancies. We had a bunch of diagnostics, event studies, randomization inference, histogram, spaghetti plots. That was like the big picture. And then we looked at, you know, the imperfect fit. And with the imperfect fit, you know, we saw really there was the demeaning one, but then the augmented really seemed to dominate it. It's just that that had to introduce this negative weighting. And I think probably my statement would be a lot of people don't care about the negative weighting. You know, if you're running regressions, then by definition, you don't really care about the negative weighting. So, because that's what it's doing. Well, there's not really a common support assumption. Len asks about the common support assumption. If you don't have covariate balance, probably that would be, you know, that would be the version of the common support, I guess, breaking down. So, you know, if you don't have common support in a matching framework, you know, you've got to use outcome regression. You know, that's the only way around it, because, or you use some sort of bias correction, which will have an outcome model anyway. So there's like, if you don't have common support in a matching, you typically have to go into that extrapolation stuff, regression-based solutions. That's what they're doing here. They don't call it common support. I mean, it's funny, like a lot of the term, they do sort of use common support language a little bit. They'll talk about, they do. So I think that would be, so that would be like my response, I guess, is that the framing of this as covariate imbalance, that could be because the units are so dissimilar. I have to keep thinking about all the ways that would map onto it, but that, I would say, roughly speaking, this, what you're talking about with common support violations, that's probably leading you into augmented synth, just to kind of cut to the chase. Are there comparison? Oh, well, they have different assumptions. So you really can't like compare them. I mean, if parallel trends holds and the factor model doesn't hold, you know, I'm not really positive if you can there'll be data generating processes, you know, where you'll see, I've never seen anybody, I did see an undergraduate thesis where someone did do matrix completion versus all of the new robust stiffened diffs under some different data generating processes, and sort of was trying to check, but I've not seen, and it will show up in the synth methods. You'll see people compare synthetic control, augmented synthetic control with 2A fixed effects. But I haven't seen it with any of the diff and diffs that don't use that. So I'm not really sure. You know, synth doesn't use a parallel trend assumption. You have parallel trends, you're good. I typically see people kind of go into synthetic control. I typically, I mean, I think it's very difficult to figure out, you know, which of those you would use if you really are indifferent. I mean, that's where it all comes down to originally. Well, you're probably not going to use diff and diff if you have one treated unit. We did in our paper, because there are papers that'll do it, but we did in our paper. But a lot of the times, historically, they just seemed like they never were competing with each other. Because yeah, like one treated unit, or you'd have a bunch of treated units, and people just were like diff and diff versus synth. But you're right that synthetic control has evolved so much that you're really pulling your hair out as to which one to use. Do you want to use one of these synth methods, or do you want to use one of these diff and diff methods? And you know, it's a good question. I mean, technically, I've played around a lot with one of these synth methods with simulations. I can't figure out with this one synth method that we'll talk tomorrow about. I cannot figure out a situation where where it's working and diff isn't working. So I mean, there's like probably a lot of value to generating a bunch of data generating processes where you get parallel trends, but you cannot do one of these other methods like synth or matrix completion. That would probably be really valuable, but I haven't really seen anybody do it. I mean, there is a new paper, there is a new survey article by Hito Imbens on causal panel estimators, but he's got a section on synth and he's got a section on diff and diff, but I've not seen these people. I've not seen anybody really put them head to head like one of those robot challenges. That would be valuable. Tried to do it on the Substack, but I've like not gotten very far. Huh. Winchin, I'm gonna have to think about that. I don't know of that. That's sort of a big question about. I'm not sure how you would do what you're describing. You're using it. I'm not positive. Let me think about that. Get back to you, or we'll talk about it tomorrow. I'm gonna let you guys go because I've kept you over for 15 minutes. But Winching, if you want to keep asking me questions about it, it'll give me something to think about tonight. If you want to describe for me like specifically what you're thinking, and I'll try to follow what you're talking about and give it some thought. Okay. All right. Hope you guys are hanging in there. All right, I'll see you in the morning. We'll do some more synthetic control. Bye-bye.